Cosmic filaments and voids are the largest and most dramatic structures in the universe, a vast interconnected tapestry of matter and emptiness that stretches across hundreds of millions of light years. Their formation is a story that is intimately tied to the deepest and most mysterious components of our cosmos. It is a story that begins with the faint, quantum whispers of the early universe and unfolds over billions of years, choreographed by the silent and relentless hand of gravity. The primary architect of this grand cosmic structure is dark matter, the mysterious, invisible substance that is thought to make up about 85% of the matter in the universe. While it does not emit, absorb, or reflect light, and therefore cannot be seen directly, its gravitational influence is everywhere. In the early universe, which was an almost perfectly smooth and uniform soup of matter and energy, there were tiny quantum fluctuations in density. The regions that were slightly denser than average had a slightly stronger gravitational pull. Over cosmic time, this tiny advantage was amplified. These denser regions began to pull in more and more matter, both dark and normal, from their surroundings, a process known as gravitational instability. This is a classic rich-get-richer scheme. The clumping of dark matter, which does not interact with light and is therefore not subject to the outward pressure of radiation, was particularly efficient. It formed a kind of invisible gravitational scaffolding, a cosmic web upon which the normal baryonic matter that we are made of could later accumulate. Over billions of years, this process has sculpted the universe into the intricate and beautiful structure we see today. The dense, high-traffic intersections of this web are the great clusters of galaxies. The long, connecting highways are the cosmic filaments. And the vast, empty regions that have been cleared out by this gravitational migration of matter are the cosmic voids. These filaments are not just passive conduits. They are the active birthplaces of galaxies. They are vast reservoirs of the primordial hydrogen and helium gas that is the raw fuel for star formation. As this gas is funneled along the filaments and into the dense nodes of the cosmic web, it can cool, condense, and collapse under its own gravity to form new generations of stars and galaxies. The voids, on the other hand, are the great silent deserts of the cosmos, places where the cosmic story is playing out in a much slower and more solitary key. The study of this large-scale structure is not just a matter of cosmic cartography. It is a powerful tool for probing the fundamental properties of our universe. The precise statistical properties of the cosmic web, the size of the voids, the thickness of the filaments, the degree of clustering of the galaxies are sensitive probes of the universe's history and its composition. By comparing our detailed, three-dimensional maps of this structure with the predictions of our cosmological models, we can measure, with incredible precision, the amount of dark matter in the universe, the nature of the primordial density fluctuations that seeded the structure, and, most excitingly, the history of the universe's expansion. The way that these structures have grown over time is a direct measure of the cosmic tug-of-war between the attractive force of gravity, which tries to pull things together, and the repulsive force of dark energy, the mysterious entity that is causing the expansion of the universe to accelerate. By studying the subtle distortions in the cosmic web, we are, in a sense, taking the pulse of the universe, measuring its vital signs, and trying to understand its ultimate fate. Will the expansion continue to accelerate forever, tearing the cosmic web apart in a big rip? Or will gravity eventually win out, causing the universe to collapse back on itself in a big crunch? The answers to these ultimate, existential questions are written in the faint, ancient light of the distant galaxies and in the grand, silent, and beautiful architecture of the cosmic filaments and voids. The cosmic web, with its intricate lacework of filaments and voids, is the fundamental organizing principle of the universe on the largest scales. The filaments are the great cosmic rivers of matter, long and often sinuous, structures that can stretch for hundreds of millions of light years. They are the arteries of the cosmos, channeling the flow of galaxies, of gas, and of dark matter between the great dense cities of the galaxy clusters. The voids, on the other hand, are the vast, underdense, and almost empty oceans that separate these cosmic continents. They are the largest, and in a sense, the simplest, structures in the entire universe, some of them spanning over 1 billion light years in diameter. To understand the origin and the evolution of this grand cosmic architecture, we must turn to our standard and remarkably successful lambda-cold dark matter model of cosmology. This model is built on a few simple ingredients. It assumes that the universe is governed by Einstein's theory of general relativity, and that it is composed of 3 main components: a small amount of normal baryonic matter, a much larger amount of cold dark matter, and a dominant component of dark energy, which is responsible for the accelerating expansion of the universe. The model also assumes a specific set of initial conditions, a universe that was, in its very first moments, in an incredibly hot, dense, and nearly uniform state, with a specific and very subtle pattern of primordial density fluctuations, the kind that is naturally produced by the theory of cosmic inflation. When we feed these simple ingredients and initial conditions into a powerful supercomputer and let the laws of physics play out over 14 billion years of simulated cosmic time, what emerges is a universe that looks remarkably like our own. The simulation shows how the tiny primordial density fluctuations are amplified by gravity. The dark matter, being the dominant gravitational component, collapses first, forming a vast, interconnected, web-like scaffolding. The normal baryonic matter is then pulled into the deep gravitational wells of this dark matter web, where it cools, condenses, and forms the galaxies we see today. The result is a universe where the galaxies are not scattered randomly, but are arranged in a beautiful filamentary pattern, a pattern that is a direct and macroscopic fossil of the microscopic quantum fluctuations of the primordial universe. The study of cosmic filaments and voids is therefore a powerful way to test and to refine this standard cosmological model. By precisely measuring the statistical properties of the cosmic web, we can place tight constraints on the properties of dark matter and dark energy. The voids are a particularly clean and powerful probe. Because they are so underdense, their evolution is dominated by the repulsive force of dark energy, making them a sensitive barometer of the cosmic acceleration. The subtle distortions in the shapes of voids, for example, can be used to measure the growth of cosmic structure over time, providing a powerful test of general relativity on the largest scales. And the galaxies that do exist within the voids, the lonely, isolated inhabitants of the cosmic deserts, are fascinating objects in their own right. They have evolved in a very different environment than their cousins in the dense, crowded filaments and clusters. They have experienced fewer mergers and interactions, and they have had a more quiescent star formation history. They are, in a sense, a more pristine, and perhaps more primitive, population of galaxies. A window into what our own Milky Way might have looked like if it had not been part of the bustling and often violent cosmic metropolis of the local group. The cosmic web, with its beautiful interplay of the full and the empty, of the dense and the diffuse, of the filaments and the voids, is a profound and elegant expression of the fundamental laws of our universe. It is a structure that connects the quantum and the cosmos, the beginning of time with its end, and the visible world of galaxies with the invisible, and ultimately dominant, dark sector of our reality. The cosmic filaments are not just a passive structural scaffolding. They are the active and dynamic arteries of the cosmic web, the primary sites of galaxy formation and evolution. They are vast and often turbulent, reservoirs of the primordial gas that is the raw fuel for creating new stars and new worlds. And the way that this gas flows along and into the filaments is a key part of the story of how galaxies like our own came to be. In the early universe, the gas was distributed relatively smoothly. But as the dark matter scaffolding of the cosmic web began to form, this gas was pulled by gravity into the deepening potential wells of the filaments. This did not happen in a gentle, uniform way. The gas fell into the filaments at supersonic speeds, creating powerful accretion shocks at the edges of the filaments, where the infalling gas was heated to millions of degrees. This hot, diffuse, and X-ray emitting gas is known as the warm-hot intergalactic medium, and it is thought to contain a significant fraction, perhaps even the majority, of all the normal baryonic matter in the modern universe. But for galaxies to form, this hot gas must be able to cool. And within the filaments, a new and beautiful process takes over. The gas does not just sit in the filament, it flows along it, like a river, towards the denser, nodal regions where the galaxy clusters are forming. And as it flows, it can cool and condense, in a process that is often referred to as cold stream accretion. These are like cold, dense, and narrow tributaries flowing through the larger, hotter river of the filament. And it is within these cold streams that the conditions become right for the formation of the first small protogalaxies. These protogalaxies are then carried along with the flow, like logs in a river, and they can merge and grow, eventually forming the larger spiral and elliptical galaxies we see today. The filaments in this picture are the cosmic nurseries, the places where the building blocks of galaxies are both formed and assembled. This process is not a simple one-way street. The galaxies that form within the filaments are not passive recipients of this gas. They are active and often violent. Participants in the cosmic ecosystem, the powerful winds from massive stars and the explosive energy from supernova explosions can blow a portion of the gas back out of the galaxy and into the surrounding filament, a process known as galactic feedback. The supermassive black holes that reside in the centers of most galaxies can also be powerful engines of feedback, launching powerful jets of plasma that can heat up the gas in the filament and prevent it from cooling and forming new stars. There is a complex and still poorly understood feedback loop, a cosmic scale process of self-regulation, where the galaxies are both built from the filaments and, in turn, shape the properties of the filaments themselves. The cosmic filaments are a new and exciting frontier in our understanding of galaxy evolution. For decades, our models of galaxy formation have been largely focused on the internal processes within a single, isolated dark matter halo. But we are now beginning to realize that the larger cosmic environment, the fact that a galaxy is living in a dense, gas-rich filament or a sparse, empty void, plays a crucial, and perhaps even a dominant, role in shaping its destiny. The study of these cosmic rivers of matter, through a combination of large-scale, multi-wavelength observational surveys and sophisticated hydrodynamic computer simulations, is one of the most vibrant and rapidly advancing fields in modern astrophysics. It is a field that is connecting the grand architectural beauty of the cosmic web with the detailed and often messy physics of star formation, of black hole growth, and of the ongoing and beautiful cosmic cycle of matter. The relationship between the vast, empty cosmic voids and the dense, matter-rich cosmic filaments is a dynamic and complementary one, a cosmic yin and yang that together define the large-scale structure of our universe. The voids are not just the absence of filaments. They are an active and essential part of the cosmic web. Their properties and their evolution providing a unique and powerful window into the fundamental nature of our cosmos. The formation of these two contrasting structures is a direct consequence of the laws of gravity, In the early universe, regions that were slightly denser than average began to attract more and more matter, their gravitational pull growing stronger over time. This is the process that formed the filaments and the clusters, but for every particle that was pulled into a growing filament, a particle was left behind in a region that was slightly less dense than average. These underdense regions, with their weaker-than-average gravitational pull, were, in a sense, the losers in the cosmic gravitational competition. As the matter around them was evacuated to form the filaments, these regions became emptier and emptier, growing into the vast cosmic voids we see today. The contrast between the two is stark. The filaments are the bustling, crowded, and dynamic cities of the cosmos, places of constant interaction, of mergers, of furious star formation. The voids, on the other hand, are the great, silent, and quiescent rural landscapes. The galaxies that exist within the voids, the so-called void galaxies, are a rare and special population. They have lived their lives in a state of profound isolation, largely free from the gravitational harassment and the frequent mergers that are the norm for their cousins in the filaments. This has had a profound impact on their evolution. Void galaxies tend to be smaller, bluer, and more gas-rich than their cluster counterparts. They have had a more placid and more continuous star formation history. They are, in a sense, cosmic fossils, a glimpse of what galaxies might look like if they were allowed to evolve in a state of splendid isolation, without the constant, and often violent, influence of their cosmic environment. But the voids are more than just a pristine laboratory for studying galaxy evolution. They are also a powerful probe of fundamental cosmology. Because they are so underdense, their dynamics are dominated not by the gravity of matter, but by the repulsive force of dark energy. The way that the voids grow and expand over cosmic time is one of our most direct and sensitive measures of the properties of dark energy. By precisely mapping the shapes and the sizes of voids at different epochs in the universe's history, we can trace the history of the cosmic acceleration and can test whether dark energy is a simple cosmological constant or something more dynamic and more complex. The voids can also be a powerful tool for testing our understanding of gravity itself. Some modified gravity theories, which have been proposed as an alternative to dark energy, predict that the law of gravity should be different in the low-density environment of a void than it is in the high-density environment of a galaxy or a cluster. By studying the subtle motions of the galaxies on the edges of voids and the weak gravitational lensing of background light by the sparse matter within them, we can place tight constraints on these alternative theories of gravity. The study of the cosmic voids is a beautiful example of how, in science, there can be as much to be learned from the absence of things as there is from their presence. These great, silent, and seemingly empty regions of our universe are not voids of information. They are, in fact, rich and eloquent storytellers, whispering to us the deepest secrets of dark energy, of gravity, and of the grand, beautiful, and ongoing story of cosmic evolution. The mapping of the cosmic web, with its intricate network of filaments and voids, is one of the great observational triumphs of modern cosmology. It is a task of immense scale and difficulty, a cosmic cartography that requires us to measure the three-dimensional positions of millions, and soon billions, of galaxies scattered across a significant fraction of the sky. The primary tool for this is the Galaxy Redshift Survey. By taking a spectrum of the light from a distant galaxy, astronomers can measure the amount by which its light has been stretched, or redshifted, by the expansion of the universe. According to Hubble's law, this redshift is a direct measure of the galaxy's distance from us. By combining this distance measurement with the galaxy's position on the sky, we can create a true three-dimensional map of the universe. The Sloan Digital Sky Survey, which began in the year 2000, was the first, and is still the most famous, of these large-scale redshift surveys. Over the last 2 decades, it has measured the redshifts of several million galaxies, creating the first, detailed, and truly stunning maps of the large-scale structure in our local cosmic neighborhood. These maps revealed, for the first time in a direct and unambiguous way, the beautiful web-like pattern of the cosmos, the long, sinuous filaments, the dense, compact clusters, and the vast, empty voids. But optical redshift surveys, like the SDSS, have their limitations. They can only see the galaxies, the luminous tracers of the cosmic web. But the vast majority of the matter in the filaments is dark matter, and a significant fraction of the normal. Baryonic matter is in the form of a hot, diffuse, and largely invisible gas. To map these dark components of the cosmic web, we need other, more subtle techniques. Gravitational lensing is one of the most powerful of these. As we have seen, the gravity of the matter in a cosmic filament, both dark and baryonic, will bend and distort the light from the more distant galaxies that lie behind it. By measuring the tiny correlated distortions in the shapes of millions of background galaxies, a technique known as cosmic shear, we can create a map of the intervening and largely invisible mass distribution. This is a powerful and beautiful way to see the dark matter scaffolding of the cosmic web. Another, and complementary, technique is to look for the faint signature of the gas in the filaments. The hot, million-degree gas in the warm-hot intergalactic medium is too diffuse to be seen directly in X-rays, except in the very densest regions, but it can be detected in absorption through its effect on the light from even more distant objects, like quasars. The ultraviolet light from a background quasar will be absorbed at specific wavelengths by the ions of different elements in the intervening filamentary gas, creating a forest of absorption lines in the quasar's spectrum. By studying this cosmic web forest, we can map the distribution, the temperature, and the chemical composition of the diffuse baryonic gas that traces the filaments. And in the future, with the immense sensitivity of new radio telescopes like the Square Kilometre Array, we may be able to map the cosmic web in a new way by detecting the faint radio emission from the neutral hydrogen gas that still exists in the less dense parts of the filaments. This multi-pronged, multi-wavelength approach, which combines the direct mapping of the galaxies, the gravitational lensing of the dark matter, and the absorption line studies of the gas, is giving us an increasingly complete and beautifully coherent picture of the grand and largely invisible architecture of our universe. It is a picture that is not just aesthetically pleasing, but is also a rich and powerful source of information about the fundamental physics that has shaped our cosmic home. The cosmic web, that vast and largely invisible network of filaments and voids, is more than just a static architectural feature of our universe. It is a dynamic, evolving ecosystem that plays a crucial and active role in the birth, the life, and the death of galaxies. The filaments are the great cosmic nurseries, the places where the raw materials for galaxy formation are concentrated and processed. The voids are the great cosmic deserts, places of solitude and quiescence. The difference between growing up in the bustling, crowded metropolis of a cosmic filament and the quiet, rural isolation of a cosmic void has a profound and lasting impact on the life of a galaxy. The primary way in which the cosmic web influences galaxy formation is through the supply of fuel. A galaxy needs a continuous supply of cold, dense gas to form new stars, and the filaments are the primary conduits for this cosmic fuel. The cold, dense streams of gas that flow along the filaments can feed the growing galaxies that are embedded within them, triggering and sustaining furious bursts of star formation. Galaxies in the dense, nodal regions of the web, where multiple filaments intersect, are particularly well fed. and they tend to be the most massive and most actively star-forming galaxies in the universe. But the cosmic web does not just feed galaxies. It can also starve them. As a galaxy falls into the dense, hot environment of a galaxy cluster at the node of the web, it can be subjected to a process called ram pressure stripping. As the galaxy moves at high speed through the hot, dense gas of the cluster, its own, colder, star-forming gas can be stripped away, like the scarf of a motorcyclist being blown off by the wind. This can rapidly quench the galaxy's star formation, turning it from a vibrant, blue, star-forming spiral into a red, dead, and passive elliptical. The cosmic web also shapes galaxies through the process of mergers and interactions. The filaments are the high-traffic highways of the cosmos. The galaxies that live within them are much more likely to have close encounters and to merge with their neighbors than the isolated galaxies in the voids. These mergers are dramatic and often violent events. They can trigger intense bursts of star formation. They can disrupt the beautiful spiral structure of a galaxy, and they can fuel the growth of the supermassive black holes that reside in their centers. The hierarchical assembly of galaxies, the process by which large galaxies are built up from the merging of smaller ones, is a process that happens primarily within the dense and dynamic environment of the cosmic filaments. The cosmic web, then, is a grand cosmic sorting machine. It is a machine that is constantly separating galaxies into different environments, and in doing so, is shaping their evolution in profoundly different ways. The study of this environmental dependence of galaxy properties is one of the most active and exciting fields in modern extragalactic astronomy. It is a field that is connecting the largest scales of the cosmos with the smallest scales of star formation and black hole accretion. And it is a field that is giving us a new, more holistic, and more ecological understanding of the life of a galaxy, an understanding that recognizes that a galaxy is not an isolated island, but is a product of its deep and constant interaction with the vast and beautiful cosmic web in which it is embedded. The formation of the cosmic filaments themselves is a story of gravitational collapse on a grand cosmic scale. It is a story that begins with the tiny and almost imperceptible quantum fluctuations of the primordial universe and ends with the majestic and beautiful architecture of the cosmic web. The key to understanding this story lies in the subtle and often counterintuitive nature of gravity in an expanding universe. In a static universe, any region that was slightly denser than average would immediately begin to collapse under its own gravity. But in an expanding universe, this gravitational attraction must compete with the overall, outward, Hubble flow of the cosmic expansion for a density fluctuation to grow. Its self-gravity must be strong enough to overcome this expansion. In the early universe, which was dominated by radiation, this was a difficult task. The pressure of the radiation itself acted to resist the gravitational collapse. But the dark matter, which does not interact with radiation, was free to begin its slow, inexorable process of gravitational clumping. After the universe became transparent to light, at the time of recombination, the normal baryonic matter was finally freed from the pressure of the radiation, and it began to fall into the deep and pre-existing gravitational wells of the dark matter halos. The growth of structure was now in full swing, but the growth was not uniform in all directions. The primordial density fluctuations were not all perfect spheres. They were a random and complex field of peaks, valleys, and saddle points, and the subsequent gravitational evolution of this field is a beautiful and highly nonlinear process. The regions that were initially the densest, the high peaks of the primordial landscape, collapsed first, and they collapsed in all three dimensions, forming the compact and roughly spherical halos that would later host the great clusters of galaxies. The regions that were slightly less dense, the ones that were shaped more like elongated ridges in the primordial landscape, would collapse first along their shortest axis and then along their second shortest axis, forming the long and often sinuous filaments of the cosmic web. And the regions that were the least dense of all, the great valleys of the primordial landscape, would expand in all three directions, becoming the vast and nearly empty voids. This is the Zeldovich pancake, or top-down picture of structure formation, and it provides a beautiful and intuitively appealing picture of how the complex web-like geometry of the cosmos can naturally emerge from the simple and well-understood physics of gravitational instability. The filaments in this picture are the places where the cosmic collapse has happened in two dimensions, but not yet in the third. They are, in a sense, the pancakes of the cosmos. The clusters are the places where the collapse has happened in all three dimensions. They are the meatballs, and the whole thing, as the saying goes, is a kind of cosmic spaghetti and meatballs. This is, of course, a highly simplified picture. The real process of structure formation is much more complex, a chaotic, and often violent, process of mergers, of accretion, and of feedback. But the fundamental, underlying principle, the idea that the beautiful and seemingly complex architecture of the cosmic web is a natural and almost inevitable consequence of the simple and elegant law of gravity acting on the tiny, quantum seeds of the primordial universe, is one of the most profound and most beautiful insights of modern cosmology. The dark matter that forms the invisible, gravitational scaffolding of the cosmic web is one of the most profound and most enduring mysteries in all of science. We know, with a very high degree of certainty, that it exists. We can see its gravitational influence everywhere, from the rotation of our own galaxy to the lensing of distant quasars. We know that it makes up about 85% of the matter in the universe. We know that it is cold, meaning it was moving slowly in the early universe. We know that it is dark, meaning it does not interact with light. But we have, as of yet, no idea what it is. The search for the identity of the dark matter particle is one of the great and most urgent quests of modern physics, a quest that is being pursued on three complementary frontiers. The first is the direct detection frontier. The idea here is that our own solar system is moving through the vast dark matter halo of the Milky Way galaxy. This means that there should be a constant wind of dark matter particles passing through the Earth and through our bodies every second of every day. These particles interact so weakly that we do not feel them, but very, very rarely. One of them might happen to collide with the nucleus of an atom in a very sensitive detector, deep underground. These direct detection experiments are marvels of low background physics. They are built in the deepest mines and tunnels in the world to shield them from the constant rain of cosmic rays that bombard the Earth's surface. They use ultra-pure materials and a host of clever techniques to distinguish a potential and incredibly rare dark matter signal from the more mundane and far more common signals from natural radioactivity. So far, despite decades of searching and a steady increase in the sensitivity of these experiments, no definitive, unambiguous signal of dark matter has been found. The second frontier is indirect detection. The idea here is that if dark matter particles can collide with each other, they might annihilate, producing a shower of more familiar standard model particles, like gamma rays, neutrinos, or antimatter particles. We can then search for an excess of these annihilation products coming from regions of the universe where we expect the density of dark matter to be very high, like the center of our own galaxy, or the hearts of nearby dwarf galaxies. A number of space-based and ground-based telescopes are dedicated to this search. There have been a number of tantalizing, and as yet unexplained, excesses of gamma rays and antimatter particles observed, but none of them has, as of yet, risen to the level of a definitive, smoking gun discovery of dark matter annihilation. The third frontier is production at particle colliders. The idea here is to create dark matter particles in the high-energy collisions of a particle accelerator, like the Large Hadron Collider. Since the dark matter particles are invisible, we cannot detect them directly, but we can look for their signature in the form of missing energy, puroti. If we see a collision that produces a spray of normal particles that are all recoiling against something that is invisible, something that has carried away a significant amount of energy and momentum, then that something could be a pair of newly created dark matter particles. This is a very challenging search, as there are many, more mundane, standard model processes that can also produce missing energy. But the LHC is continuing to push the limits of this search, exploring new and higher energy regimes. The quest to identify the dark matter particle is a journey into the unknown, a journey into the dark sector of physics. The leading theoretical candidate for the dark matter particle is the WIMP, or weakly interacting massive particle, a hypothetical particle that would have been produced in the hot early universe and would have just the right interaction strength to leave behind the observed cosmic abundance of dark matter today. But the fact that we have not yet found the WIMP, despite decades of searching, has led many to consider other, more exotic possibilities. Perhaps dark matter is not a WIMP, but an action, a very light and very weakly interacting particle that was originally proposed to solve a different puzzle in particle physics. Or perhaps the dark sector is not so simple. Maybe it is not just a single particle, but a whole zoo of different dark particles, with their own complex dark forces, a shadow world that interacts with our own only through the gentle and persistent touch of gravity. The mystery of dark matter is a profound and humbling reminder of how much we still have to learn about the fundamental constituents of our universe and its eventual discovery. Whenever and however it comes will be a revolution in our understanding of the cosmos, a revolution that will open up a new and previously invisible chapter in the beautiful and endlessly fascinating story of reality. The distribution of matter in the universe, the way that galaxies are arranged in the vast cosmic web of filaments and voids, is a direct and beautiful reflection of the initial conditions of the universe and the fundamental laws of physics that have governed its evolution. The density of matter is the key parameter that drives this process. In the early universe, which was an almost perfectly smooth and uniform soup, there were tiny and almost imperceptible quantum fluctuations in density. These fluctuations were the seeds of all the structure we see today. The regions that were slightly denser than average had a slightly stronger gravitational pull, and over the 14 billion years of cosmic history, they have grown into the dense, matter-rich filaments and clusters of the cosmic web. The regions that were slightly less dense than average had a weaker gravitational pull, and they have been evacuated of matter, growing into the vast and nearly empty cosmic voids. The density of matter, then, is the primary driver of cosmic structure formation. But the type of matter also plays a crucial role. The dark matter, which makes up the vast majority of the matter in the universe, interacts only through gravity. It is collisionless. This means that it can clump and cluster very efficiently, without being subject to the pressure of radiation or the complexities of gas dynamics. It is the dark matter that forms the primary, underlying, and invisible scaffolding of the cosmic web. The normal baryonic matter, on the other hand, is much more complex. It can interact with light. It can form atoms and molecules. It can cool and condense. It can be heated by stars and by black holes. The baryonic matter is, in a sense, a more active and more colorful participant in the cosmic drama. It is pulled into the deep gravitational wells of the dark matter halos, but once there, it has a life of its own. It can cool and collapse to form the dense, star-forming disks of spiral galaxies. It can be heated and shocked in the violent process of galaxy mergers. It can be stripped away as a galaxy falls into the hot, dense environment of a cluster. The complex interplay between the gravitational pull of the dark matter and the complex hydrodynamical and radiative processes of the baryonic matter is what gives rise to the rich and often beautiful diversity of the galaxies we see in the universe. The density of matter, both dark and baryonic, is not just a static property, it is a dynamic, evolving quantity. As the universe expands, the overall average density of matter decreases, but the density, contrast, the difference between the dense regions and the underdense regions grows over time. The rich get richer, and the poor get poorer. The filaments become more filamentary. The voids become more void-like. This process of gravitational amplification of the initial density fluctuations is the engine of cosmic evolution. And by studying the way that this structure has grown over cosmic time, by mapping the distribution of galaxies and the properties of the cosmic web at different epochs in the universe's history, we can perform a powerful and precise test of our entire cosmological model. We can measure, with incredible accuracy, the total amount of matter in the universe, the relative proportions of dark and baryonic matter, and the nature of the primordial density fluctuations from which all of this structure arose. The density of matter, then, is more than just a number. It is a key, a Rosetta Stone, that allows us to decipher the long, beautiful, and complex story of our own cosmic origins. The story of the cosmic web, of the formation of the filaments and the voids, is a story that is beautifully and powerfully captured by a few primary and well-established theoretical frameworks. At the foundation of this story is the Big Bang Theory, the idea that our universe began in an incredibly hot, dense, and rapidly expanding state. This theory provides the overall evolutionary context, the expanding space-time background upon which the drama of structure formation plays out. The next and crucial theoretical ingredient is the concept of cosmic inflation. As we have seen, inflation is the idea that the universe underwent a period of hyper-accelerated exponential expansion in its very first moments. This is a crucial part of the story for two reasons. First, it explains the large-scale smoothness and flatness of our universe, the seemingly special initial conditions that are required for a universe like ours to exist. Second, and even more profoundly, it provides a natural and beautiful physical mechanism for generating the initial seed density fluctuations from which all the structure in the universe later grew. The tiny and unavoidable quantum fluctuations in the inflaton field during this period were stretched to astronomical scales, becoming the primordial ripples in the density of the early universe. The specific statistical properties of these fluctuations, their near, but not perfect, scale invariance, are a unique and now well-confirmed prediction of the inflationary paradigm. With these initial conditions in place, the rest of the story is largely a matter of gravity. The lambda-cold dark matter model is our standard and remarkably successful theory of how these initial small fluctuations grow over cosmic time to form the complex web-like structure we see today. The cold dark matter part of the model is the idea that the dominant component of the matter in the universe is a new and as yet undiscovered type of particle that was moving slowly in the early universe and interacts only through gravity. It is the gravitational pull of this dark matter that is the primary engine of structure formation. The lambda part of the model refers to the cosmological constant, the energy of the quantum vacuum, the dark energy that is responsible for the accelerating expansion of the universe in the present day. This dark energy has a profound and, in a sense, a destructive impact on the growth of structure. Its repulsive, anti-gravitational force is now beginning to dominate over the attractive force of gravity, and it is in the process of shutting down the formation of new, large-scale structures in the universe. The cosmic web is, in a sense, being frozen in place by the accelerating expansion. These three theoretical pillars, the Big Bang, cosmic inflation, and the LCDM model of structure formation, together form our standard and incredibly powerful model of cosmology. It is a model that can explain, with a stunning degree of precision, a vast range of different and independent astronomical observations, from the detailed statistical properties of the cosmic microwave background to the large-scale distribution of galaxies and the observed history of cosmic expansion. And yet, it is a model that is also, in a very real sense, profoundly incomplete and deeply mysterious. We do not know what the dark matter is, we do not know what the dark energy is, and we do not have a final, complete theory of the inflationary epoch. Our standard model of cosmology is a magnificent and towering intellectual edifice, but it is an edifice that is built on a foundation of profound and beautiful ignorance. The cosmic filaments, those vast and largely invisible rivers of matter, are not just the structural backbone of the universe, they are also the primary conduits for the flow of the normal baryonic matter that makes up the stars, the planets, and ourselves. The story of how this baryonic matter is accreted onto and processed within the filaments is a key part of our understanding of how galaxies are born and how they grow. In the early universe, the baryonic matter, which is mostly hydrogen and helium gas, was smoothly and uniformly distributed. But as the dark matter scaffolding of the cosmic web began to form, this gas was pulled by gravity into the deepening potential wells of the filaments. This process of cosmic accretion did not happen in a gentle, quiescent way. The gas fell into the filaments at supersonic speeds, creating vast and powerful accretion shocks at the boundaries of the filaments. These shocks heated the infalling gas to millions of degrees, creating a hot, diffuse, and X-ray emitting plasma that is known as the warm-hot intergalactic medium. This WIM is thought to contain a very significant fraction of all the baryonic matter in the universe, and it is a major, and as yet largely unmapped, component of the cosmic ecosystem. But for galaxies to form, this hot gas must be able to cool and to condense. And within the filaments, a new and more subtle process takes over. The gas does not just sit in the filament, it flows along it towards the denser nodal regions of the web. And in the very densest, central parts of the filaments, a process of cold stream accretion can occur. These are narrow and relatively cold, streams of gas that can penetrate deep into the hot halo of a growing galaxy, delivering a direct and efficient supply of fuel for star formation. This is now thought to be the primary way in which massive, star-forming galaxies in the early universe acquired their gas. But the story of the baryons is a story of a cosmic cycle, a cycle of inflow and outflow. The baryonic matter that is accreted from the filaments and forms stars within a galaxy does not just stay there. The powerful and often violent process of star formation itself can drive a portion of this gas back out of the galaxy. The combined effect of the radiation pressure from massive, young stars and the explosive energy from supernova explosions can create a powerful galaxy-scale superwind, a wind that can blow a significant fraction of a galaxy's gas back out into the surrounding intergalactic medium of the filament. This process of galactic feedback is a crucial and still poorly understood part of the story. It is a self-regulation mechanism that can quench star formation, that can enrich the intergalactic medium with the heavy elements that are forged in the stars, and that can profoundly shape the evolution of the galaxy and its cosmic environment. The supermassive black holes at the centers of galaxies are another, and even more powerful source of feedback. As gas is accreted onto these black holes, a tremendous amount of energy can be released, often in the form of powerful relativistic jets of plasma. These jets can plow into the surrounding gas in the galaxy and in the filament, heating it up and preventing it from cooling and forming new stars. This active galactic nucleus feedback is now thought to be the primary mechanism that is responsible for shutting down star formation in the most massive galaxies in the universe. The story of the baryonic matter in the cosmic web is a complex and beautiful story of a cosmic ecosystem. It is a story of accretion and of feedback, of inflow and of outflow, of a constant and dynamic cycling of matter between the galaxies and the vast filamentary reservoirs of the intergalactic medium. It is a story that is connecting the largest scales of cosmology with the smallest scales of stellar and black hole physics. And it is a story that we are only just beginning to be able to read through the combined power of our most advanced multi-wavelength telescopes and our most sophisticated hydrodynamical computer simulations. The cosmic filaments are not just the places where galaxies are born, they are also the places where they live, where they interact, and where they evolve. The environment of a dense cosmic filament is a very different place from the quiet, solitary environment of a cosmic void. And this difference has a profound and lasting impact on the properties of the galaxies that inhabit these different regions. The primary way in which the filamentary environment shapes galaxy evolution is through the increased frequency of gravitational interactions. The filaments are the crowded, high-traffic highways of the cosmos. The galaxies that live within them are much more likely to have close encounters, to gravitationally harass, and to ultimately merge with their neighbors. These galaxy mergers are some of the most dramatic and transformative events in the life of a galaxy. When two gas-rich spiral galaxies collide and merge, their interstellar gas can be compressed and shocked, triggering a furious and often galaxy-wide burst of star formation. A starburst. This can rapidly consume the galaxy's gas supply and can, over time, transform it from a blue, star-forming, disk-dominated galaxy into a red, passive, and spheroid-dominated elliptical galaxy. The merger can also fuel the growth of the supermassive black holes at the centers of the two galaxies, and the subsequent powerful feedback from these accreting black holes can further help to shut down star formation. The process of hierarchical galaxy formation, the idea that large galaxies are built up from the merging of smaller ones, is a process that is driven by and happens primarily within the dense and dynamic environment of the cosmic filaments. But the filamentary environment can also shape galaxies in more subtle ways. As a galaxy moves through the hot, diffuse gas of the warm-hot intergalactic medium that permeates the filament, it can be subject to a gentle but persistent ram pressure that can slowly strip away its own, colder outer halo of gas. This can reduce its fuel supply for future star formation, a process known as strangulation. The filamentary environment can also affect the spin of a galaxy. The large-scale tidal gravitational fields within a filament can exert a torque on a growing protogalaxy, causing it to acquire an angular momentum. This is now thought to be the primary source of the rotation of the large, spiral disks of galaxies like our own Milky Way. And there is even evidence that the spins of galaxies are not randomly oriented, but are preferentially aligned with the direction of their host filament. A beautiful and large-scale manifestation of the underlying gravitational dynamics of the cosmic web. The study of this environmental dependence of galaxy properties of the deep and intimate connection between a galaxy and its place in the cosmic web is one of the most active and exciting frontiers in modern extragalactic astronomy. It is a field that is giving us a new, more holistic, and more ecological understanding of the life of a galaxy, an understanding that recognizes that a galaxy's destiny is not just determined by its own internal properties, but is profoundly shaped by its deep and constant interaction with the vast and beautiful cosmic ecosystem in which it lives. The vast sea and nearly empty cosmic voids, the great silent deserts of the cosmos, are more than just the absence of matter. They are a unique and powerful laboratory for testing our understanding of some of the deepest and most profound mysteries of our universe, including the nature of dark energy. Dark energy, as we have seen, is the mysterious and dominant component of the universe that is responsible for the accelerating expansion of space-time. But its true nature remains a profound enigma. Is it the cosmological constant, the constant and irreducible zero-point energy of the quantum vacuum? Or is it something more dynamic, a new, evolving energy field that we have called quintessence? Or is it a sign that our understanding of gravity itself is incomplete? The voids are a perfect place to try and distinguish between these different possibilities. The reason for this is that the voids are, by their very definition, regions where the density of matter, both dark and baryonic, is very low. This means that their dynamics are not dominated by the attractive force of gravity, but by the repulsive and pervasive force of dark energy. The way that the voids grow and evolve over cosmic time is a very sensitive probe of the properties of dark energy. In a universe with a simple cosmological constant, the voids should grow in a specific, predictable way. But in a universe with a more dynamic, quintessence-like dark energy, their growth could be different. By precisely mapping the shapes and the sizes of a large sample of voids at different epochs in the universe's history, using the data from large-scale galaxy redshift surveys, we can, in principle, measure this growth history and can place tight constraints on the equation of state of dark energy, the parameter that tells us how its pressure relates to its density. This is a powerful and completely independent way to probe the nature of dark energy, a way that is complementary to the more traditional methods that use supernova and the cosmic microwave background. The voids can also be used to test our understanding of gravity itself. Some modified gravity theories, which have been proposed as an alternative to dark energy, predict that the law of gravity should be different in the very low-density environment of a void than it is in the high-density environment of our own solar system, where general relativity has been tested with incredible precision. By studying the subtle and often anomalous motions of the few galaxies that do exist within the voids, and the weak gravitational lensing of background light by the sparse matter within them, we can search for these potential and revolutionary deviations from Einstein's theory. The study of the cosmic voids is a beautiful example of the power of null experiments in science. By studying the places where nothing is happening, we can learn a tremendous amount about the fundamental and often invisible rules that govern the places where something is. The great, silent, and seemingly empty voids of our universe are not, in fact, silent at all. They are whispering to us, in their own subtle and beautiful language, the deepest secrets of dark energy, of gravity, and of the ultimate fate of our cosmic home. The detailed and often beautiful computer simulations of the formation and the evolution of the cosmic web are one of the great and often unsung triumphs of modern computational astrophysics. These simulations are not just pretty pictures, they are powerful and essential tools for understanding the complex and highly nonlinear physical process that have shaped our universe. They are the crucial theoretical bridge that connects the simple initial conditions of the early universe with the rich and complex tapestry of galaxies, filaments, and voids that we observe today. A modern cosmological simulation is a monumental computational undertaking. It begins with a large representative box of the universe, which is filled with a vast number of particles that represent the dark matter. The initial conditions for these particles are set by the predictions of the theory of cosmic inflation, a nearly uniform distribution with a specific and very subtle pattern of primordial density fluctuations. The simulation then evolves this system forward in time, step by tiny step, calculating the gravitational force between every single particle at each step, and moving the particles accordingly. This is a task that requires a massive supercomputer, often running for months on end, to track the complex gravitational dance of billions, and sometimes trillions, of dark matter particles over the full 14 billion year history of the universe. The result of such a dark matter-only simulation is a stunning and beautifully detailed picture of the formation of the dark matter scaffolding of the cosmic web, a picture that can be directly and quantitatively compared with the large-scale structure that we observe in our galaxy surveys. But to understand the formation of the galaxies themselves, we need to add the complex, and often messy, physics of the normal, baryonic matter. This is the realm of hydrodynamical simulations, which, in addition to tracking the gravity of the dark matter, also solve the equations of fluid dynamics for the cosmic gas. These simulations must include a host of other complex physical processes: the way the gas cools by radiating away its energy, the way it collapses to form stars, the way that the energy from these stars and from supernova explosions can heat the gas and drive it out of the galaxy in powerful winds, and the way that the supermassive black holes at the centers of galaxies can grow and can inject a tremendous amount of energy back into their surroundings. The creation of these subgrid models for these complex, small-scale processes is one of the greatest challenges in computational astrophysics. But when it is done right, the result is a stunning and often breathtakingly realistic simulation of a living, breathing, and evolving cosmic ecosystem. A simulation that can be directly compared with the detailed, multi-wavelength observations of real galaxies from telescopes like Hubble and the James Webb Space Telescope. These simulations are not just for making pretty movies. They are an essential and indispensable part of the scientific process. They allow us to test our theoretical ideas in a controlled and repeatable way. They allow us to explore the complex and often unexpected consequences of our physical models. And they allow us to make detailed, quantitative predictions that can be used to guide the design of our next generation of telescopes and observational surveys. The beautiful and intricate dance of cosmic structure formation is a process of immense complexity. And it is only through the powerful and beautiful partnership between the observational astronomer, the theoretical physicist, and the computational astrophysicist that we can hope to one day fully understand and to fully appreciate the deep and elegant story of how our universe and our own galactic home came to be. The growth of the cosmic web, the process by which the initial small-density fluctuations of the early universe are amplified by gravity into the vast and complex structures of today, is a process that is governed by a few key and fundamental cosmological parameters. The measurement of these parameters with the highest possible precision is one of the primary goals of modern observational cosmology. The first, and perhaps most important, of these is the initial density fluctuation amplitude, a number that sets the overall lumpiness of the early universe. If this number were much larger, structure would have formed much earlier and much more violently. perhaps leading to a universe that is dominated by supermassive black holes. If it were much smaller, structure would have formed much more slowly, and the universe might still be a smooth and largely featureless soup of gas and dark matter. The fact that this number has the value it does, about 1 part in 100,000, is one of the key, and as yet unexplained, fine-tunings of our universe. The next key parameter is the total amount of matter in the universe and its division into dark matter and baryonic matter. The total matter density determines the overall strength of gravity, and therefore the overall rate at which structure grows. The relative amount of baryonic matter is also crucial, as it is the baryons that are responsible for all the complex and often dissipative gas physics that leads to the formation of the luminous galaxies we see. The expansion rate of the universe, as described by the Hubble constant and the properties of dark energy, is another critical parameter. The expansion of the universe is a force that works against gravity, trying to pull things apart. The growth of structure is a delicate and cosmic scale, balancing act between the attractive force of gravity and the repulsive, outward push of the cosmic expansion. The precise history of this expansion, whether it was decelerating in the past and is accelerating now, has a profound impact on the final statistical properties of the cosmic web. And finally, there are the more subtle, but equally important parameters that describe the statistical nature of the primordial density fluctuations themselves. Are they Gaussian, meaning they have a simple bell curve-like statistical distribution? Or do they have some non-Gaussian component, some hint of a more complex and non-random process in the very early universe? And what is the spectral index? The parameter that describes how the amplitude of the fluctuations depends on their physical scale. All of these parameters, and a few others, together define our standard cosmological model, the LCDM model. And the remarkable and beautiful fact is that this simple 6-parameter model is able to explain, with a stunning degree of precision, a vast and diverse range of different astronomical observations, from the detailed statistical properties of the cosmic microwave background to the large-scale distribution of galaxies and the observed history of cosmic expansion. The measurement of these fundamental cosmological parameters through a combined analysis of all these different and independent observational probes is one of the great and ongoing triumphs of modern precision cosmology. It is a process that has transformed cosmology from a largely speculative and often philosophical field into a mature, quantitative, and data-driven science. And it is a process that is continuing to push the boundaries of our knowledge, searching for the small and subtle cracks in this standard model that could point the way to a new, deeper, and more complete understanding of the fundamental and beautiful laws that have governed the birth, the life, and the ultimate destiny of our cosmic home, the vast and largely invisible. Cosmic filaments are more than just the structural backbone of the universe. They are also a powerful and often disruptive influence on the motion and the evolution of the galaxies that are embedded within them. The gravitational field of a filament is not a simple, spherical one. It is a complex, and often highly anisotropic, tidal field. A galaxy that is living within a filament is not just being pulled towards the center of the filament. It is also being stretched and torqued by the large-scale gravitational environment. This can have a profound impact on the galaxy's dynamics. It can, for example, induce the formation of bars and spiral arms in the disks of spiral galaxies. It can also affect the spin of a galaxy, the direction of its angular momentum. There is a growing body of evidence, from both observations and simulations, that the spins of galaxies are not randomly oriented, but are preferentially aligned with the direction of their host filament. This spin alignment is a beautiful and large-scale manifestation of the underlying gravitational dynamics of the cosmic web. It is as if the galaxies are like tiny spinning tops that have been set in motion by the great cosmic river of the filament in which they are flowing. The motion of galaxies along the filaments is another key and dynamic aspect of the cosmic web. The filaments are the great cosmic highways, channeling the flow of galaxies from the underdense voids towards the dense and ever-growing galaxy clusters at the nodes of the web. The galaxies that are in these filamentary flows are often moving at very high speeds, hundreds or even thousands of kilometers per second. And as they move, they can interact with and merge with their neighbors. This process of hierarchical merging is a key driver of galaxy evolution, particularly in the dense environment of the filaments. But the filamentary environment is not just about gravity. It is also about gas. The filaments are vast reservoirs of the hot, diffuse, warm-hot intergalactic medium. A galaxy that is moving at high speed through this medium can be subject to a powerful ram pressure that can strip away its own, colder, star-forming gas. This can effectively quench the galaxy's star formation, turning it from a vibrant blue spiral into a red, dead elliptical. The cosmic filaments, then, are a place of profound and often violent transformation. They are the places where galaxies are born, where they are fed, where they interact, where they are harassed, and where they are ultimately transformed. The study of the motion and the evolution of galaxies within the cosmic web is a new and exciting frontier in astrophysics. It is a field that is connecting the grand and often abstract principles of cosmology with the detailed and often messy physics of galaxy formation, and it is a field that is giving us a new, more holistic and more ecological understanding of the life of a galaxy, an understanding that recognizes that a galaxy's destiny is not just written in its own internal stars, but is also profoundly shaped by the great cosmic river of the filament in which it is, for a time, a beautiful and often turbulent passenger. The cosmic microwave background, that faint and nearly uniform glow of ancient light that fills our entire sky, is more than just a baby picture of the universe. It is also a powerful and incredibly subtle backdrop against which we can see the shadows of the large-scale structures in the more recent and more local cosmos. The interaction between the CMB photons and the vast and nearly empty cosmic voids is a beautiful example of this. The voids, as we have seen, are the most underdense regions of the universe. This means that the gravitational potential within a void is slightly higher than the average potential of the universe. This has a subtle but measurable effect on the CMB photons that pass through it, an effect known as the integrated Sachs-Wolf effect. As a CMB photon enters a void, it has to climb out of the gravitational well of the surrounding denser filament. In doing so, it loses a tiny amount of energy, and its wavelength is slightly blue-shifted. As it then travels through the void and begins to fall into the gravitational well of the filament on the other side, it gains that energy back, and it is redshifted back to its original wavelength. In a static, non-expanding universe, these two effects would perfectly cancel each other out, and there would be no net effect on the photon's energy. But we live in an accelerating, dark energy-dominated universe. This means that in the time it takes the photon to cross the void itself has expanded and has become slightly emptier, and the gravitational potential wells on its edges have become slightly shallower. This means that the photon gains slightly less energy back on its way out of the void than it lost on its way in. The net effect is a tiny, but real, decrease in the photon's energy, a tiny, additional redshift. This means that the CMB, when viewed through a large cosmic void, should appear to be slightly, but measurably, colder than the average. This cold spot signature of the cosmic voids in the CMB has, in fact, been detected by cross-correlating the maps of the CMB temperature with the maps of the large-scale structure from galaxy surveys. This is a stunning and beautiful discovery. It is a direct and completely independent confirmation of the existence of dark energy and the accelerating expansion of the universe. It is a detection that relies on the subtle and beautiful interplay between the largest and most empty structures in the universe and the oldest and most ancient light. The voids are not just empty spaces, they are active and eloquent participants in the cosmic story, their very emptiness leaving a faint, cold, and beautiful shadow on the afterglow of creation itself. The existence of the vast and beautifully structured cosmic web of filaments and voids is a cornerstone of our modern cosmological model. And the evidence for its existence is now overwhelming, coming from a diverse and beautifully concordant set of different and independent observational probes. The first and most direct line of evidence comes from the large-scale galaxy redshift surveys. As we have seen, these surveys have allowed us to create the first true three-dimensional maps of the distribution of galaxies in our local cosmic neighborhood. And these maps have revealed, with a stunning and unambiguous clarity, the intricate and beautiful filamentary, web-like structure of the cosmos. But these surveys only trace the luminous tip of the iceberg of the cosmic structure. The vast majority of the matter in the web is dark. To see this invisible dark matter scaffolding, we must turn to the subtle and powerful technique of gravitational lensing. By measuring the tiny and statistically coherent distortions in the shapes of millions of background galaxies, we can create a map of the intervening and largely invisible mass distribution. And these weak lensing maps have confirmed, with a beautiful and independent power, the predictions of the LCDM model. They show that the dark matter is indeed distributed in a vast, interconnected cosmic web, with the luminous galaxies acting as faithful, if biased, tracers of this underlying dark scaffolding. The third line of evidence comes from the study of the cosmic microwave background itself. The tiny and beautiful temperature fluctuations in the CMB are the primordial seeds from which the entire cosmic web later grew. The statistical properties of these fluctuations, their power spectrum, contain a wealth of information about the initial conditions of the universe and the predictions of the inflationary LCDM model for how these initial small fluctuations should evolve over 14 billion years into the large-scale structure we see today are in stunning agreement with the observed properties of the galaxy distribution. It is a beautiful and powerful causal chain that connects the quantum fluctuations of the first infinitesimal moments of the universe with the majestic and beautiful architecture of the cosmic web of today. And finally, there are the more subtle, but equally powerful, probes that come from the study of the intergalactic medium, the diffuse gas that fills the spaces between the galaxies. The Lyman alpha forest of absorption lines in the spectra of distant quasars, the faint X-ray emission from the hot gas in galaxy clusters, the Sunyaev-Zeldovich effect, which is the scattering of CMB photons by the hot electrons in this gas, all of these different and independent observational techniques are providing us with an increasingly detailed and beautifully coherent picture of the baryonic component of the cosmic web. The story of the discovery of the cosmic web is a story of a beautiful and powerful scientific convergence. It is a story where the data from a host of different and independent lines of inquiry have all pointed towards the same, single, and beautifully coherent picture of our cosmic home. It is a testament to the power of the scientific method to piece together, from a collection of faint and often subtle cosmic clues, a grand and beautiful narrative of our own cosmic origins. The distribution of galaxies in the universe, the way they are arranged in the vast and beautiful cosmic web, is not a static architectural feature. It is the dynamic and ever-evolving product of the fundamental physical processes that have shaped our cosmos. The interplay between the initial conditions of the early universe, the gravitational pull of dark matter, and the complex hydrodynamical behavior of the normal, baryonic matter is what gives rise to the rich, and often beautiful, diversity of the galactic population. The cosmic filaments are the great cosmic rivers, the places where the density of both dark and baryonic matter is high, and it is in these dense and dynamic environments that the life of a galaxy is most profoundly shaped. The filaments are the places where galaxies are born, where they are fed, where they interact, and where they are ultimately transformed. The continuous and often turbulent flow of cold gas along the filaments provides the raw fuel for star formation, allowing the galaxies that live within them to grow and to shine. The high density of galaxies within the filaments also means that gravitational interactions and mergers are a common and often transformative part of a galaxy's life. These mergers can trigger spectacular and often galaxy-wide bursts of star formation. They can disrupt the delicate spiral structure of a disk galaxy, transforming it into a more chaotic and spheroid-dominated elliptical galaxy. And they can funnel gas towards the supermassive black hole at the galaxy's center, fueling its growth and triggering the powerful and often self-regulating feedback that can shut down star formation for good. The cosmic voids, on the other hand, are the great cosmic deserts, the few galaxies that are born in or that wander into these vast and nearly empty regions of space live a very different and much more solitary life. They are starved of the fresh, cold gas that fuels star formation in the filaments. They are free from the constant and often violent gravitational harassment of their neighbors, and so they tend to evolve in a much more quiescent and much more predictable way. They are the cosmic control group, the baseline against which we can measure the profound and often transformative impact of the filamentary environment on the life of a galaxy. The distribution of galaxies in the universe, then, is a story of a grand cosmic segregation. It is a story of how the initial and very subtle density fluctuations of the early universe have been amplified by gravity into a vast and beautiful landscape of cosmic continents and oceans, of bustling galactic metropolises and quiet rural backwaters. And it is a story that is giving us a new, more holistic and more ecological understanding of the life of a galaxy, an understanding that recognizes that a galaxy is not an island, entire of itself, but is a piece of the continent, a part of the main. The formation of the vast and nearly empty cosmic voids is a story of a gentle and large-scale cosmic evacuation. It is a process that is driven not by an explosive outward push, but by a slow, persistent, and large-scale gravitational pull. The voids are not the result of some cosmic explosion that has pushed the matter out. They are, rather, the natural and unavoidable consequence of the gravitational growth of the dense, filamentary structures around them. The story begins in the early universe, with the primordial and very subtle density fluctuations that were imprinted on the cosmos during the period of inflation. These fluctuations were a random, Gaussian field with peaks, valleys, and saddle points. The voids are the descendants of the largest and deepest of these primordial valleys, the regions that started out with a slightly lower than average density of matter. In an expanding universe, gravity is in a constant tug of war with the overall Hubble expansion, Hubble. For a structure to grow, its self-gravity must be strong enough to overcome this cosmic stretch. In the overdense regions, the peaks of the primordial landscape, gravity was strong enough to win this battle. These regions began to collapse, to decouple from the Hubble flow, and to form the bound, virialized halos of the dark matter that would later host the galaxies and the clusters. But in the underdense regions, the voids, gravity was not strong enough to win. These regions did not collapse. In fact, they expanded even faster than the average universe. And as the matter around them was pulled away into the growing gravitational wells of the surrounding filaments and clusters, these underdense regions became even emptier, their internal gravity even weaker, and their expansion even faster. This is a beautiful and self-reinforcing feedback loop. The voids are not just empty, they are actively evacuating themselves, pushing their sparse contents out towards the denser and more gravitationally attractive walls of the cosmic web. The distinction between a small void and a large void is, in a sense, a matter of scale and of evolutionary history. The small voids are the result of the local gravitational dynamics of the cosmic web, the empty spaces that are left behind as smaller group-scale filaments form and merge. The large supervoids, on the other hand, are the true primordial deserts of the cosmos, the direct descendants of the largest and deepest underdensities of the initial inflationary field. They are a more pristine and more direct window into the initial conditions of our universe. The study of the formation and the evolution of the voids is a rich and rapidly developing field of cosmology. It is a field that is providing us with a new and powerful set of tools for probing the fundamental properties of our universe, from the nature of dark energy to the statistical properties of the primordial inflationary fluctuations. And it is a field that is giving us a new and deeper appreciation for the beautiful and often surprising role that emptiness itself has played in the grand and ongoing story of cosmic structure formation. The age of the universe at the time of filament formation is a crucial and often overlooked parameter in the story of the cosmic web. The filaments we see in the local modern universe are the old, mature, and well-developed descendants of a much more tenuous and much more chaotic structure that existed in the early cosmos. The story of filament formation is a story of a gradual and hierarchical process of assembly in the very early universe, just a few 100 million years after the Big Bang. The cosmic web was a much more fine-grained and much more interconnected structure. The first, small and proto-filaments formed as the dark matter began to collapse along the ridges of the primordial density field. These early filaments were the sites of the formation of the first, small, dwarf galaxies. As the universe continued to expand and to evolve, these small early filaments were themselves pulled together by gravity. They merged and they accreted onto each other, forming larger and more massive filamentary structures. This is the hierarchical aspect of structure formation. The cosmic web is not a static structure that was formed all at once. It is a dynamic and constantly evolving ecosystem, a system that has been building itself from the bottom up over the entire 14 billion year history of the universe. The age of the universe then has a profound impact on the properties of the filaments. The young filaments of the early universe were denser, they were more gas-rich, and they were the sites of much more intense and much more chaotic star formation. The old, mature filaments of the modern universe are more diffuse. They are dominated by the hot and largely sterile, warm-hot intergalactic medium, and the galaxies within them are, for the most part, older, redder, and more passively evolving. By studying the properties of the filaments at different redshifts, at different epochs in the universe's history, we can, in a sense, watch a movie of the cosmic web as it assembles itself. This is one of the primary goals of the large-scale galaxy redshift surveys. By mapping the distribution of galaxies at different distances, and therefore at different look-back times, we can create a series of snapshots of the cosmic web at different ages, and by comparing these snapshots with the predictions of our cosmological simulations, we can perform a powerful and precise test of our entire hierarchical model of structure formation. The age of the universe at the time of filament formation is not just a single number. It is a rich and complex story. A story of a universe that has been constantly and beautifully building itself from a state of primordial, quantum simplicity to the vast, intricate, and majestic architectural wonder of the modern cosmic web. The Sloan Digital Sky Survey is a project of monumental scale and of profound scientific significance. It is a project that has, more than any other, transformed our understanding of the large-scale structure of the universe and has turned the abstract theoretical concept of the cosmic web into a tangible and beautifully detailed observational reality. Launched in the year 2000, the SDSS has used a dedicated 2.5-meter telescope at the Apache Point Observatory in New Mexico to conduct a systematic and multifaceted survey of a large fraction of the northern sky. It has done this in two complementary ways. First, it has taken deep, multicolor digital images of the sky, creating a vast and beautiful atlas of over 100 million galaxies. This imaging survey has provided us with an unprecedented, two-dimensional view of the cosmic landscape. But the true revolutionary power of the SDSS lies in its spectroscopic survey. By taking a detailed spectrum of the light from a subset of these galaxies, the survey has been able to measure their redshifts with high precision. And as we have seen, this redshift is a direct measure of a galaxy's distance. By combining the position of a galaxy on the sky with its distance, the SDSS has been able to create the first large-scale and truly three-dimensional maps of the universe. And it is in these maps that the majestic and beautiful architecture of the cosmic web was, for the first time, revealed in all its glory. The long, sinuous filaments, the dense, compact clusters at their intersections, and the vast and nearly empty voids in between all of these features, which had previously been seen only in the abstract, pixelated world of computer simulations, were now seen in the real observational data. It was a moment of profound scientific confirmation, a moment when our theoretical understanding of the cosmos was shown to be, in its broad strokes, beautifully and powerfully correct. The SDSS has been more than just a map-making machine. The vast and publicly available data set that it has produced has become a treasure trove for the entire global astronomical community, fueling a veritable explosion of research in almost every area of extragalactic astronomy and cosmology. It has been used to study the properties of galaxies and their dependence on their cosmic environment. It has been used to discover and to characterize thousands of distant quasars, the luminous, active black holes that are the lighthouses of the early universe. It has been used to find the faint, ghostly streams of stars that are the remnants of the dwarf galaxies that have been tidally disrupted by our own Milky Way, providing a direct and beautiful confirmation of the hierarchical, merger-driven growth of our own galactic home. And it has been used to perform some of the most precise and most powerful tests of our standard cosmological model, the subtle and beautiful. Wiggles in the large-scale distribution of the galaxies, the baryon acoustic oscillations that are a fossilized remnant of the sound waves that propagated through the early universe, have been detected with high significance in the SDSS data. providing a powerful and independent standard ruler with which we can measure the expansion history of the universe and the properties of dark energy. The Sloan Digital Sky Survey is a project that has truly and irrevocably changed our view of the universe. It is a testament to the power of a large, systematic, and collaborative approach to science. And it is a project whose legacy will continue to shape the course of astronomy and cosmology for many decades to come. The challenge of distinguishing between the different and often overlapping components of the cosmic web, the dense, virialized clusters, the more tenuous and often sinuous filaments, and the vast and nearly empty voids is one of the key and often difficult tasks of modern observational cosmology. These are not, in reality, discrete and cleanly separated objects. They are all part of a single, continuous, and multi-scale density field. And the development of robust and objective mathematical and statistical algorithms for identifying and for characterizing these different environments is a major and active area of research. The simplest and most traditional way to identify a galaxy cluster is to look for a significant and statistically improbable overdensity of galaxies in a small region of the sky. But this galaxy counting method has its limitations. It can be affected by projection effects, where a chance alignment of several smaller groups of galaxies along the line of sight can mimic the appearance of a single, massive cluster. A more robust method is to look for the hot X-ray emitting gas that fills the deep, gravitational potential well of a true massive cluster, but this requires deep and often expensive observations with an X-ray space telescope. The identification of the filaments is an even greater challenge. They are, by their very nature, much more diffuse and much more elongated than the compact clusters, a number of different and often highly sophisticated. Algorithms have been developed to try and trace these filamentary structures in our galaxy redshift surveys. Some of these are based on graph theory, treating the galaxies as nodes in a network and searching for the long and interconnected chains that represent the filaments. Others are based on the geometry of the density field itself, using techniques that are borrowed from the fields of medical imaging and computer vision to identify the ridgelines and the watersheds of the cosmic landscape. And the voids are, in a sense, the easiest structures to identify. They are simply the large and nearly empty regions that are left over after all the galaxies and the clusters have been accounted for. But even here, there are subtle and important questions of definition. How empty does a region have to be called a void? And what is the best way to define the shape of these often complex and non-spherical regions? The development of these structure-finding algorithms is a beautiful example of the deep and often fruitful interplay between theoretical cosmology, observational astronomy, and the more abstract worlds of mathematics, of statistics, and of computer science. And the ultimate goal of all of this is to create a detailed and quantitative cosmic census, a catalog of the properties of the different large-scale environments in the universe. This will allow us to perform a precise and powerful statistical test of our cosmological models and to study, in a rigorous and quantitative way, the profound and beautiful impact that these different cosmic environments have on the birth, the life, and the ultimate destiny of the galaxies that live within them. The great and gravitationally bound clusters of galaxies which sit at the dense and high-traffic intersections of the cosmic web are the largest and most massive cities of the cosmos. They are vast and often violent ecosystems containing hundreds or even thousands of individual galaxies, all orbiting within a common and incredibly deep gravitational potential well. The story of how these cosmic metropolises are assembled and how they grow is a story that is intimately and inextricably linked to the story of the cosmic filaments that feed them. A galaxy cluster is not a static object that was formed all at once. It is a dynamic and constantly growing entity, a structure that has been assembling itself over the entire 14 billion year history of the universe, through the hierarchical merging of smaller groups and individual galaxies. And the cosmic filaments are the primary and preferential conduits for this cosmic accretion. The galaxies, the gas, and the dark matter of the universe are not falling into the clusters uniformly from all directions. They are being funneled into them along the great cosmic rivers of the filaments. This has a profound and observable impact on the properties of the clusters themselves. A young and still forming cluster will often have a clumpy and irregular shape with multiple dense substructures that correspond to the smaller groups that are in the process of merging. An old and relaxed cluster, on the other hand, will have a much smoother and more spherically symmetric distribution of galaxies, a sign that it has had time to gravitationally digest its most recent meals. The gas within a galaxy cluster is also a powerful tracer of this ongoing process of accretion. The vast majority of the normal baryonic matter in a cluster is not in the galaxies themselves, but is in the form of a hot and incredibly diffuse intracluster medium, a plasma that is heated to tens of millions of degrees and that glows brightly in the X-ray part of the spectrum. As a new group of galaxies falls into the cluster along a filament, its own colder gas can be shock-heated and stripped away, becoming part of the hot ICM. This process can leave a long and often spectacular tail of stripped gas, a beautiful and direct visual record of the galaxy's recent and often traumatic journey into the heart of the cluster. The relationship between the filaments and the clusters is a symbiotic and a co-evolutionary. 1. The clusters are formed from the material that is funneled into them by the filaments. And the powerful gravitational and hydrodynamical processes that are at play within the clusters, the mergers, the stripping, the feedback from the supermassive black holes can, in turn, have a profound impact on the properties of the filaments in their immediate vicinity. The study of the interface between the filaments and the clusters is a new and exciting frontier in our understanding of the cosmic web. It is a place where the large-scale and relatively gentle dynamics of the cosmic accretion flows meet the small-scale and often violent physics of galaxy and cluster evolution. And it is a place where we can see, in a direct and beautiful way, the grand and ongoing story of how the universe is building its largest and most majestic structures. The cosmic star formation rate, the rate at which the universe as a whole is converting its primordial gas into new stars, is one of the most fundamental and most revealing of all cosmological observables. It is a measure of the creative activity of the cosmos, a cosmic vital sign that tells us about the health and the evolution of the universe's galactic population. And the story that this cosmic star formation rate tells is a dramatic one, a story of a brilliant and youthful cosmic noon, followed by a long, slow, and inexorable decline into a more quiescent and more passive old age. The cosmic star formation rate was very low in the first billion years or so of the universe's history. The cosmic dawn, when the first small proto-galaxies were just beginning to form, it then rose dramatically, reaching a peak at a redshift of about 10 billion years ago. This was the cosmic noon, the period when the universe was at its most active, its most creative, its most vibrant. The galaxies at this time were gas-rich. They were undergoing frequent mergers, and they were forming new stars at a furious and often unsustainable rate. Since that time, for the last 10 billion years, the cosmic star formation rate has been in a steady and dramatic decline. The universe, in its old age, is becoming a much more quiescent and much more red and dead place. The average galaxy in the modern universe is forming stars at a rate that is about 10 times lower than its counterpart at the cosmic noon. The cosmic voids, those vast and nearly empty regions of space, play a crucial and often overlooked role in this grand cosmic story. The voids are, by their very nature, the most sterile and the least creative regions of the universe. The density of gas within them is far too low to allow for the formation of new galaxies and new stars. They are the great cosmic deserts, the places where the fire of cosmic creation has, for the most part, been extinguished. But the voids are not just passive, empty spaces. They are also, in a sense, a cosmic time capsule. The few lonely galaxies that do exist within the voids have been largely isolated from the violent and transformative processes of merging and of feedback that have shaped the evolution of their cousins in the dense, filamentary regions. They are, in a sense, a more pristine and more primitive population of galaxies. A glimpse of what the universe might have looked like if it had not been for the powerful and often quenching influence of the dense cosmic environment. The study of the cosmic voids and of the galaxies within them is a powerful and complementary way to understand the grand and complex story of the rise and the fall of the cosmic star formation rate. It is a story that is connecting the largest scales of the cosmos with the smallest scales of star and galaxy formation. And it is a story that is giving us a new, more holistic and more ecological understanding of the life cycle of the universe itself. A story of a brilliant, youthful exuberance, followed by a long, slow, and graceful decline into a more peaceful and more contemplative old age. The cold dark matter model is the cornerstone of our modern standard theory of cosmology. It is a beautifully simple and remarkably powerful idea, and it's primary and most profound. Success is in its ability to explain, with a stunning degree of precision, the observed large-scale structure of our universe, the beautiful and intricate tapestry of the cosmic web. The key to the success of the CDM model lies in its two defining characteristics: cold and dark. Dark means that the dark matter particles do not interact with light. This is crucial. It means that in the early universe, when the normal of baryonic matter was tightly coupled to the intense bath of radiation, and was therefore subject to a strong outward radiation pressure that resisted gravitational collapse, the dark matter was not. It was free to begin its slow and inexorable process of gravitational clumping, forming the deep and pre-existing potential wells into which the baryons would later fall. Cold means that the dark matter particles were moving slowly in the early universe. Their kinetic energy was negligible compared to their rest mass energy. This is also crucial. It means that the dark matter could clump and cluster on all scales, from the smallest dwarf galaxy-sized halos to the largest cluster-sized halos. This hierarchical or bottom-up model of structure formation, where small things form first and then merge to form larger things, is a key. And now, well confirmed. Prediction of the CDM paradigm. The CDM model, when combined with the initial conditions from cosmic inflation, provides a complete and stunningly successful theoretical framework for understanding the formation of the cosmic web. The model predicts, with a high degree of statistical precision, the number of dark matter halos of a given mass, their spatial clustering, and their internal density profiles. And these predictions are in beautiful agreement with a wide range of different and independent astronomical observations, from the large-scale distribution of galaxies in our redshift surveys to the subtle and powerful signatures of weak gravitational lensing. The CDM model in this sense, is a triumph of modern theoretical cosmology. And yet, it is a triumph that is also, in a very real sense, profoundly incomplete and deeply mysterious. We still have no idea what the cold dark matter particle actually is. And on the very smallest and most challenging scales of observation, the scales of individual dwarf galaxies, there are a number of tantalizing, and as yet unresolved, discrepancies between the predictions of the simple CDM model and the observational data. These small-scale challenges, like the cusp core problem and the missing satellites problem, may be a sign that the real world is more complex, that the dark matter is not quite so simple, or that the complex and often messy physics of the baryons is playing a more important and more subtle role than our current simulations can fully capture. But despite these challenges, the cold dark matter model remains the single, most successful, and most powerful framework we have for understanding the grand and beautiful architecture of our cosmic home, and the beautiful and intricate pattern of the filaments and the voids that it so naturally and so elegantly explains is one of the most profound and most beautiful testaments to its enduring scientific power. Baryon acoustic oscillations are one of the most beautiful and most powerful of all cosmological probes. They are a fossil, a relic, an echo from the very early universe, a subtle and beautiful pattern that is imprinted on the large-scale distribution of matter in the cosmos. And they are a powerful and wonderfully precise standard ruler with which we can measure the expansion history of the universe and the properties of dark energy. The story of the BAOs begins in the first few 100,000 years after the Big Bang, when the universe was a hot, dense, and opaque plasma of baryons, electrons, photons, and dark matter. This primordial plasma was a dynamic and acoustically active medium. The photons provided a strong outward radiation pressure, while the gravity of the baryons and the dark matter provided an inward attractive force. This cosmic tug-of-war between pressure and gravity created sound waves, or acoustic oscillations, that propagated through the plasma at about 60% of the speed of light. Imagine a single primordial density fluctuation, a small, overdense region of dark matter. This overdensity would have pulled in the surrounding baryons and photons, but the intense pressure of the photons would have resisted this collapse, launching an expanding spherical sound wave of baryons and photons into the surrounding plasma. This wave would have traveled outwards for about 380,000 years, until the moment of recombination, when the universe cooled down enough for the protons and the electrons to combine and to form neutral hydrogen atoms. At this moment, the universe suddenly became transparent to light. The photons were now free to stream away, and they are what we see today as the cosmic microwave background. The pressure that was driving the sound wave suddenly vanished. The expanding spherical shell of baryons was frozen in place at a specific and predictable physical distance from the original central overdensity of dark matter. This distance, the distance that the sound wave was able to travel before recombination, is the baryon acoustic scale. And it is a true and very robust standard ruler. Its physical size, about 500 million light years, is determined by the well-understood physics of the early universe. This frozen spherical shell of baryons then began to gravitationally attract more matter, both baryonic and dark, and over the subsequent 14 billion years of cosmic history, this subtle and beautiful spherical pattern has been imprinted on the large-scale distribution of the galaxies. It means that galaxies are not just randomly clustered. They have a slight, but statistically significant, preference to be separated by a distance of about 500 million light-years. This is the BAO peak in the galaxy correlation function. By measuring the apparent angular size of this BAO standard ruler at different red shifts, at different epochs in the universe's history, we can perform a powerful and beautifully precise measurement of the expansion history of the universe. And this, in turn, is one of our most powerful probes of the nature of dark energy. The detection of the BAO peak in the large-scale galaxy surveys, like the Sloan Digital Sky Survey, has been one of the great and most beautiful triumphs of modern precision cosmology. It is a stunning confirmation of our entire cosmological model, a beautiful and direct link between the physics of the early universe and the grand and majestic architecture of the modern cosmic web. And it is a testament to the power of the human mind to read in the subtle, statistical patterns of the distant galaxies, the faint and ancient echoes of the very first sounds of the cosmos. The vast and nearly empty cosmic voids are more than just a passive and uninteresting component of the cosmic web. They are a unique and powerful laboratory for testing our most fundamental theories of gravity. Einstein's general theory of relativity has been tested with incredible precision in the strong field regime of our own solar system and in the extreme environment of binary pulsars. But how do we know that it is the correct theory of gravity on the very largest cosmological scales? The accelerating expansion of the universe, which is attributed to dark energy in the standard LCDM model, could, in principle, be a sign that general relativity itself is breaking down on these vast cosmic scales. This has led to the development of a host of modified gravity theories that alter Einstein's equations in a way that can produce a late-time cosmic acceleration without the need for any new and mysterious form of dark energy. The challenge for these theories is to do this in a way that is still consistent with the very precise tests of general relativity in our own solar system. This has led to the development of theories with screening mechanisms that ensure that the modifications to gravity are only important in the very low-density regions of the universe and are effectively screened or hidden in the high-density environment of a galaxy or a solar system. And this is where the cosmic voids become a crucial and powerful testing ground. The voids are, by their very definition, the lowest density regions of the universe. And so, it is in the voids that any potential deviations from general relativity should be most apparent. These deviations could manifest in a number of different and, in principle, observable ways. They could affect the rate at which the voids grow and expand over cosmic time. They could affect the subtle and often anomalous motions of the few galaxies that do exist within the voids, and they could affect the way that the sparse matter within the voids gravitationally lenses the light from more distant background galaxies. By precisely measuring these different and independent observational probes of the void environment, and by comparing them with the predictions of both general relativity and the various modified gravity alternatives, we can perform a powerful and unique test of the fundamental law of gravity on the largest scales of the cosmos. This is a new and exciting frontier in observational cosmology, a field that is still in its infancy, but which holds the promise of either providing a stunning, new confirmation of Einstein's beautiful theory, or perhaps of finding the first tantalizing cracks in its foundations, cracks that could point the way to a new, deeper, and more complete understanding of the fundamental nature of gravity itself. The great silent voids are a laboratory of cosmic proportions, a place where the very fabric of space-time may be whispering to us the secrets of its own, and as yet, unknown laws. The distribution of the cosmic filaments, the vast and largely invisible rivers of matter that form the backbone of the cosmic web, is not a static architectural feature that was imprinted on the universe at its birth. It is a dynamic and constantly evolving structure, a structure whose properties have changed dramatically over the 14 billion year history of the cosmos. The story of the evolution of the filaments is a story of a gradual and hierarchical process of assembly, a story of a universe that has been constantly and beautifully building itself from a state of primordial quantum simplicity to the vast and majestic complexity of the modern cosmic web. In the early universe, in the first billion years or so after the Big Bang, the cosmic web was a much more fine-grained and much more interconnected structure. The first, small, proto-filaments formed as the dark matter began to collapse along the ridges of the primordial density field. These early filaments were the sites of the formation of the first small, dwarf galaxies, and they were, in a sense, the capillaries of the cosmic circulatory system. As the universe continued to expand and to evolve, these small, early filaments were themselves pulled together by gravity. They merged and they accreted onto each other, forming larger, more massive, and more prominent filamentary structures, the arteries and the veins of the cosmic web. This is the hierarchical or bottom-up aspect of structure formation. The properties of the filaments have also evolved dramatically over cosmic time. The young filaments of the early universe were much denser, they were much more gas-rich, and they were the sites of much more intense and much more chaotic star formation. The old, mature filaments of the modern universe, on the other hand, are more diffuse. They are dominated by the hot and largely sterile, warm-hot intergalactic medium. And the galaxies within them are, for the most part, older, redder, and more passively evolving. By studying the properties of the filaments at different redshifts, at different epochs in the universe's history, we can, in a sense, watch a movie of the cosmic web as it assembles itself. This is one of the primary and most powerful goals of the large-scale galaxy redshift surveys. By mapping the three-dimensional distribution of galaxies at different distances, and therefore at different look-back times, we can create a series of snapshots of the cosmic web at different ages, and by comparing these snapshots with the detailed and beautiful predictions of our cosmological simulations, we can perform a powerful and precise test of our entire hierarchical model of structure formation. The story of the evolution of the cosmic filaments is a story of a universe that is in a constant state of becoming, a story of a cosmos that is always and beautifully under construction. It is a story that is giving us a new, more dynamic, and more profound understanding of the grand and ongoing process of cosmic evolution. The role of magnetic fields in the dynamics of the cosmic filaments is a new and exciting frontier in our understanding of the cosmic web. The universe is not just filled with matter and gravity, it is also permeated by weak, but ubiquitous, magnetic fields. The origin of these cosmic magnetic fields is still a deep and largely unsolved mystery. They may have been generated in the very early universe, during the period of inflation or in a subsequent cosmological phase transition. Or they may have been seeded by the first stars and galaxies and then amplified and spread throughout the intergalactic medium by a turbulent cosmic dynamo. Whatever their origin, these magnetic fields, even though they are incredibly weak, can have a profound impact on the physics of the diffuse and highly ionized gas that makes up the warm-hot intergalactic medium within the filaments. The magnetic fields can provide a form of magnetic pressure that can resist the gravitational collapse of the gas, potentially slowing down the process of galaxy formation. They can also affect the transport of heat and of cosmic rays through the filamentary gas, a process that is crucial for understanding the thermal and the chemical evolution of the intergalactic medium, and they can, in principle, be detected. The interaction of the magnetic fields with the free electrons in the filamentary gas should produce a faint, and very diffuse synchrotron radio emission. And as the polarized light from distant background radio sources passes through the magnetized gas of a filament, its plane of polarization should be slightly rotated, a phenomenon known as Faraday rotation. The detection of these faint and very challenging observational signatures of the filamentary magnetic fields is one of the key and most exciting goals of the next generation of powerful and highly sensitive radio telescopes, like the Square Kilometer Array. The study of cosmic magnetism is a field that is still in its infancy, but it is a field that promises to add a new and crucial layer of complexity and of beauty to our understanding of the cosmic web. It is a field that is reminding us that the universe is not just a story of gravity and of gas, but is also a rich and beautiful and largely unexplored electromagnetic tapestry. The future of our universe, as painted by our current standard cosmological model, is a story of a long, slow, and ultimately lonely decline. The accelerating expansion of the universe, driven by the mysterious and seemingly inexhaustible dark energy, is a force that is, in a very real sense, tearing the cosmic web apart. For now, the universe is still a dynamic and richly interconnected place. The filaments are still funneling galaxies into the great and ever-growing clusters. But as the cosmic acceleration continues, this process of hierarchical structure formation will grind to a halt. The clusters that have already formed will become more and more isolated from each other, their filamentary supply lines stretched and broken by the relentless and ever-increasing expansion of the voids. The galaxies that are not already part of a gravitationally bound group or cluster will find themselves on a one-way and increasingly lonely journey into the ever-expanding and ever-emptier cosmic darkness. Our own local group of galaxies is a small and gravitationally bound island in this expanding cosmic ocean. We are destined to one day merge with our large neighbor, the Andromeda Galaxy, to form a single, giant, elliptical galaxy, Milkomeda. But all the other, more distant galaxies and clusters will, one by one, recede from us at an ever-increasing speed, their light red-shifted into oblivion, until they eventually disappear beyond our cosmic event horizon. The night sky of the very far future, 1 trillion years from now, will be a dark and profoundly empty place. The only light will be the faint and aging glow of the stars within our own giant and isolated galaxy. And as these last stars burn out, as the last white dwarfs cool to a final cold blackness, as the last supermassive black holes slowly evaporate into a faint mist of Hawking radiation, the universe will settle into its final and eternal state of heat death. It will be a universe of almost perfect and almost absolute emptiness, a cold, dark, and silent void, a universe where nothing ever happens, and where the long and beautiful the story of cosmic evolution has finally and irrevocably come to an end. This is a bleak, but scientifically plausible vision of our ultimate cosmic destiny. But it is also a vision that is based on our current and necessarily incomplete understanding of the universe. The nature of dark energy, the ultimate fate of the vacuum, the possibility of new and as yet undiscovered physical laws, all of these could, in principle, change the final chapter of our cosmic story. The future, like the past, is a country that we are only just beginning to explore, and it is a country that is still full of deep and beautiful and perhaps even hopeful mysteries. The universe should not exist, and yet here it is, This simple, stark fact, when held in the mind, is perhaps the most profound and unsettling mystery we can contemplate. The prevailing scientific narrative of our cosmic origins tells a story of exquisite balance and improbable fortune. In the very first moments of the universe, in the incandescent crucible of the Big Bang, matter and its mirror image, antimatter, were forged from pure energy in almost perfectly equal amounts. But matter and antimatter are mortal enemies. When they meet, they annihilate each other in a flash of pure energy, leaving behind nothing but a sea of light. If the balance had been perfect, if for every particle of matter there had been an identical particle of antimatter, the universe would have been a short-lived and sterile affair. As it cooled, a great cosmic annihilation would have occurred, leaving behind a cold, dark, and empty cosmos, filled only with a diffuse, featureless bath of radiation. There would be no stars, no galaxies, no planets, and no people to wonder at the silence. And yet we are here. We live in a universe that is overwhelmingly, almost exclusively, made of matter. This means that somehow, in that first, fiery instant, a tiny, almost imperceptible imbalance occurred. For every billion pairs of matter and antimatter particles that were created and then destroyed, a single, solitary particle of matter was left over. It is this minuscule, 1 in a billion cosmic anomaly, this sleight of hand in the universe's initial coin toss. That is the sole reason for our existence. Everything we see, from the grandest superclusters of galaxies to the very atoms that make up our bodies, is the leftover, residual matter from that great primordial annihilation. The universe we inhabit is a cosmic rounding error. This matter-antimatter asymmetry is one of the deepest and most unsolved puzzles in modern physics. What tipped the scales? What was the subtle flaw in the universe's initial symmetry that allowed matter to gain its tiny, but ultimately decisive, victory over its antimatter twin? The answer is not yet known, but it is a question that points to a deeper and more profound truth that our very existence is predicated on a series of seemingly impossible coincidences, on a universe that seems to have won a cosmic lottery of almost unimaginable odds. The universe exists. This simple three-word statement, when deeply considered, is the wellspring of all our science, all our philosophy, all our art. We find ourselves adrift in a cosmos of immense scale, of breathtaking beauty, and of intricate, and often bewildering, complexity. It is a realm of 100 billion galaxies, each a glittering city of 100 billion stars, and on at least one small, rocky planet, orbiting one unremarkable star in a quiet, suburban spiral arm of one of these galaxies. The universe has woken up. It has produced conscious beings, beings capable of turning their gaze back upon the cosmos and asking the most fundamental question of all: why is there something rather than nothing? This is the big question, a riddle that has haunted the human mind since the dawn of thought. The state of nothingness, a complete and utter absence of all that is of matter, of energy, of space, of time, of the very laws that govern them, seems, to many, to be the simpler, more natural, and more probable state. Existence, with all its intricate machinery and its seemingly arbitrary rules, seems to be the state that requires a special explanation. It is not just a philosophical musing. It is a puzzle that is deeply embedded in the very heart of our most advanced scientific theories. Our best scientific story, the Big Bang model, provides a stunningly successful narrative of how the universe has evolved over the last 13.8 billion years, from a hot, dense, and simple initial state to the cool, complex, and structured cosmos we see today. But it cannot and does not explain why there was a universe to begin with. It does not explain the origin of the initial conditions, nor the source of the fundamental laws that allowed the story to unfold. And it is in the nature of these laws and initial conditions that the mystery deepens. The universe seems to be exquisitely and almost miraculously fine-tuned for the existence of complexity and life. The fundamental constants of nature, the strength of gravity, the charge of the electron, the mass of the proton appear to be set to values that fall within an incredibly narrow, life-permitting range. If the strong nuclear force, for example, the force that binds protons and neutrons together in atomic nuclei, were just a few percent weaker, then stable atoms heavier than hydrogen would not be able to form. The universe would be a monotonous and lifeless sea of hydrogen gas. If it were a few percent stronger, then all the hydrogen in the early universe would have fused into heavier elements, leaving no fuel for the long-lived stars, like our sun, that are necessary for the slow, patient evolution of life. The ratio of the strength of the electromagnetic force to the force of gravity is another, even more astonishing. Example: the number is immense, about 10 to the power of 40. If this ratio were significantly different, the universe would be a barren and sterile place. If gravity were much stronger, stars would burn out in a flash, collapsing into black holes before life could ever get started. If it were much weaker, then matter would never have been able to clump together to form the stars and galaxies in the first place. The list of such cosmic coincidences is long and growing. The mass of the electron, the expansion rate of the universe, the density of dark energy, all of these, and many more, seem to be balanced on a knife edge. The probability of all of these parameters falling, by pure chance, into the tiny, life-permitting sliver of the vast landscape of possibilities seems almost infinitesimally small. It is as if we have walked into a cosmic casino and found that a single, randomly thrown set of dice has come up with the same, specific, and incredibly complex winning number 1,000 times in a row. The mystery of our existence is deepened still further when we consider the nature of the vacuum, the seemingly empty space that fills the cosmos. According to the strange and beautiful laws of quantum mechanics, a true vacuum is not empty at all. It is a seething, energetic sea of virtual particles, constantly popping into and out of existence, a quantum foam that fills all of space. When physicists try to calculate the total energy density of this vacuum, they get a number that is astronomically, absurdly large. If this vacuum energy had the gravitational effect that our current theories predict, it would have caused the universe to expand at an unimaginable rate, ripping itself apart in the first fraction of a second of its existence. There would be no stable structures, no stars, no galaxies, no life. And yet, we observe that the universe is not being ripped apart. In fact, the observed energy of the vacuum, which we now associate with dark energy, is incredibly, exquisitely small, almost zero. The discrepancy between the theoretical prediction and the observed reality is a staggering 120 orders of magnitude. It is, by a wide margin, the worst prediction in the entire history of science. The fact that the vacuum energy is so tiny, that our universe is so stable, is another profound and completely unexplained cosmic coincidence. And then, there is the puzzle we began with, the asymmetry between matter and antimatter. The universe we inhabit is a universe of matter, but our best theories of the early universe predict that matter and antimatter should have been created in perfectly equal amounts. If this had been the case, they would have annihilated each other, leaving behind a cold, dark universe of pure light. The fact that we are here, that matter exists at all, is a testament to a tiny 1 in a billion imbalance that occurred in the first fiery moments of creation. The precise mechanism that produced this life-giving asymmetry remains one of the great, unsolved mysteries in all of particle physics. The question, why is there something rather than nothing, is not a question that science can yet answer. The scientific method is a powerful tool for explaining how things work, for describing the processes that unfold within a given set of rules and initial conditions. But it is not, at present, equipped to explain why those rules and conditions exist in the first place, or why there is a universe for them to apply to at all. This profound and beautiful challenge lies at the very heart of physics, of cosmology, and of philosophy, inviting us to confront the limits of our empirical knowledge, and perhaps the very nature of reality itself. The question, why is there something rather than nothing, is predicated on the assumption that nothing is a simple, straightforward, and perhaps even more natural state than something. But when we try to pin down what we actually mean by nothing, the concept quickly dissolves into a series of profound and perplexing paradoxes. It is a word that is easy to say, but almost impossible to truly conceive of. In our everyday, colloquial use, nothing often refers to an empty space. If you open a box and find it empty, you might say, there's nothing in it. But an empty box is not nothing. It is a box, a container, an object that exists in space. And the space inside the box is not nothing. It is a three-dimensional volume, a part of the geometric fabric of our universe. What if we remove the box and just consider the empty space itself? Is that nothing? Not according to modern physics. Space, as we now understand it from Einstein's general theory of relativity, is not a passive, empty stage. It is a dynamic, physical entity, a space-time that can be bent, warped, and stretched by the presence of matter and energy. It is a something in its own right. So, to get to a truer nothing, we must imagine the absence of space itself. But how can we even begin to do that? Our minds are so deeply conditioned to think in spatial terms that to imagine a state devoid of space is a cognitive feat that borders on the impossible. The moment we try to picture nothing, we inevitably picture it as a kind of black, empty void, which is itself a spatial concept. This leads us to the realm of philosophy, to the idea of an absolute nothingness. This would be a state of complete and utter non-existence. No matter, no energy, no space, no time, no physical laws, no mathematical truths, no logical principles, no consciousness, no properties, no potentiality. It would not just be the absence of all things, it would be the absence of the very possibility of things. It is a concept of such radical negation that it may be, in a deep sense, logically incoherent. The very act of defining it, of giving it a name, seems to imbue it with a kind of existence. This philosophical quagmire is why physicists, when they speak of a universe from nothing, are almost always speaking of a very different and much more well-defined concept of nothing. The nothing of modern physics is the quantum vacuum. And as we have seen, the quantum vacuum is far from being a true void. It is the lowest possible energy state of the universe's quantum fields. But this lowest energy is not zero. It is a seething, energetic sea of constant quantum fluctuations, a place where pairs of virtual particles are constantly bubbling into and out of existence. This is not a speculative idea. It is a direct consequence of the Heisenberg uncertainty principle, and its effects, like the Casimir effect, are experimentally measurable. The quantum vacuum, the nothing of physics, is a very rich and complex something. And it is from this rich and complex something that our universe is thought to have emerged. The theory of cosmic inflation posits that our universe was born from a tiny quantum fluctuation in a pre-existing high-energy false vacuum. In this scenario, the universe did not arise from an absolute philosophical nothingness. It arose from a pre-existing physical system, a quantum field, albeit one that was in a very different and unstable state. This just pushes the ultimate question back a step. Why did this false vacuum exist in the first place? Why did it have the specific properties that allowed for the birth of our universe? And what about the physical laws themselves? If absolute nothingness means the absence of everything, then it must also mean the absence of the laws of physics. So, how could a universe, with its intricate and consistent set of laws, emerge from a state where no laws existed? Did the laws somehow exist before the universe, in some abstract Platonic realm, waiting to be instantiated? If so, then these laws are themselves a form of something, and we are not starting from a true nothing. Or did the laws emerge with the universe? In which case, what was the principle that governed their emergence? This deep and tangled relationship between existence and the laws that govern it has led some philosophers and physicists to suggest that the very premise of the question is flawed. Perhaps something is the more natural, the more fundamental, the default state, and nothing is the difficult, and perhaps impossible, abstraction. The philosopher Robert Nozick, for example, speculated that nothingness might be inherently unstable, that there might be a kind of fecundity principle at play, a force that causes nothing to nothing itself, leading inevitably to the existence of something. Another related idea is that the total energy of the universe may be exactly zero. The positive energy of matter and radiation could be perfectly balanced by the negative gravitational potential energy. If this is the case, then the creation of the universe from the quantum vacuum would not violate the law of conservation of energy. It would be a free lunch, the creation of a zero-energy system from a zero-energy state. This is a beautiful and compelling idea, but it still relies on the pre-existence of the quantum vacuum and its laws. The puzzle remains. The persistent difficulty we have in even defining, let alone conceiving of, an absolute nothingness is a powerful clue. It suggests that our intuitive sense that nothing is the simpler and more natural state may be a profound and deeply ingrained cognitive error. We are beings of something, living in a universe of something, and our minds are tools that have evolved to navigate this reality. The concept of nothing, in its absolute form, may simply be a logical and psychological limit, a concept that points to the boundary of our own understanding, a boundary that we may never be able to cross. The story of our universe, as we currently understand it, begins with an event of almost unimaginable violence and creativity, the Big Bang. This is not a theory about an explosion in a pre-existing empty space. It is a theory about the beginning of space and time themselves, a theory about the evolution of our entire observable cosmos from a state of incredible and almost incomprehensible heat and density. Our scientific narrative can trace this story back to an astonishingly early moment, to a time just a tiny, infinitesimal fraction of a second after the beginning. At the Planck epoch, a time of roughly 10 to the power of minus 43 seconds, the entire observable universe was compressed into a space smaller than a single atomic nucleus. The temperature was a staggering 10 to the power of 32 Kelvin. In this primordial crucible, the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces are thought to have been unified into a single, symmetric superforce. Our current laws of physics, the separate theories of general relativity and quantum mechanics, break down at this extreme scale. We do not yet have a complete theory of quantum gravity that can describe this earliest of all epochs. What happened at the precise moment of time zero, or what, if anything, came before it, remains the deepest and most profound mystery in all of science. But from the Planck epoch onwards, the story begins to come into sharper focus. The universe then entered a period of astonishing, hyper-accelerated expansion, a period known as cosmic inflation. Between roughly 10 to the power of minus 36 and 10 to the power of minus 32 seconds, the universe expanded exponentially, growing by a factor of at least a trillion in the blink of an eye. This incredible stretching of the fabric of space-time smoothed out any initial irregularities and flattened its geometry, elegantly explaining the observed uniformity and flatness of our universe today. And most profoundly, inflation took the tiny, unavoidable quantum fluctuations of the primordial vacuum and stretched them to astronomical scales, planting the seeds for all the large-scale structure, the galaxies and the clusters of galaxies that we see today. At the end of inflation, the immense energy of the inflaton field that had been driving the expansion was converted into a hot, dense, and uniform soup of fundamental particles and radiation, an event known as reheating. This is the true, fiery beginning of the hot Big Bang phase of the universe's evolution, as the universe continued its rapid, but now more sedate, expansion. It began to cool. In the first few microseconds, the universe was a quark-gluon plasma, a state of matter so hot that even protons and neutrons could not exist. But as the temperature dropped, the quarks began to freeze out, binding together under the influence of the strong nuclear force, to form the first protons and neutrons. It was at this crucial early stage that a tiny, and still unexplained, asymmetry between matter and antimatter occurred. For every billion antiquarks, roughly one extra quark was created. This tiny 1 in a billion imbalance is the reason that our universe is made of matter and not just a sea of light. Over the next few minutes, in a process known as Big Bang nucleosynthesis, the protons and neutrons began to fuse together, forging the nuclei of the lightest elements. The universe at this time was like a vast cosmic nuclear reactor. The precise outcome of this primordial fusion was a universe made of roughly 75% hydrogen and 25% helium, with trace amounts of lithium. The remarkable agreement between these theoretical predictions and the observed abundances of these elements in the oldest stars is one of the most powerful and beautiful pieces of evidence for the Big Bang theory. For the next 380,000 years, the universe remained a hot, dense, and opaque plasma. The temperature was so high that electrons could not bind to the newly formed atomic nuclei. This sea of free electrons acted like a dense fog, constantly scattering photons of light, making the universe impenetrable to our view. But as the universe continued to expand and cool, it eventually reached a temperature of about 3,000 Kelvin. At this point, the electrons had slowed down enough to be captured by the nuclei, forming the first stable, neutral atoms of hydrogen and helium. This event is known as recombination. Suddenly, the cosmic fog lifted, the universe became transparent to light. The photons that had been trapped in the plasma were now free to travel unimpeded through space, and they have been traveling ever since. Their wavelength stretched and cooled by the subsequent 14 billion year-long expansion of the universe, from high-energy visible light into the cool, faint microwaves that we detect today. This is the cosmic microwave background, the oldest light in the universe, a beautiful uniform glow that comes to us from all directions in the sky. It is a baby picture of our universe, a snapshot of the moment it first became transparent, a fossil that carries with it a wealth of information about the conditions of the early cosmos. Following the release of the CMB, the universe entered a period known as the Dark Ages, which lasted for several 100 million years. There were not yet any stars or galaxies to light up the cosmos. The universe was a vast, dark, and slowly evolving expanse of neutral hydrogen and helium gas. But it was not perfectly uniform. The tiny density fluctuations that had been imprinted during inflation were still there. And gravity, the patient and relentless architect of the cosmos, was beginning to go to work. The slightly denser regions began to attract more and more gas from their surroundings, their gravitational pull growing ever stronger. Over hundreds of millions of years, these collapsing clouds of gas became hot enough and dense enough at their centers to ignite the first nuclear fires. The first stars were born. The cosmic dark ages were over. The light was turned on. These first stars were likely very different from the stars we see today. They were forged from the pure, primordial gas of the Big Bang, and were therefore made of only hydrogen and helium. They were likely incredibly massive, hundreds of times the mass of our Sun, and they lived short, violent, and spectacular lives. In their fiery cores, they began the process of stellar nucleosynthesis, fusing the light elements into the heavier elements that are essential for the formation of planets and life: carbon, oxygen, nitrogen, iron. When these first massive stars died in spectacular supernova explosions, they scattered these newly forged elements into the interstellar medium, enriching the gas clouds from which the next generation of stars would be born. And so, the cosmic cycle of creation began. Gravity continued to pull these first stars and the enriched gas that surrounded them together, forming the first small dwarf galaxies. And these dwarf galaxies, in turn, merged and collided over billions of years, building up the grand spiral and elliptical galaxies like our own Milky Way that we see today. The story of the Big Bang is a story of profound and beautiful transformation. It is the story of how, from a state of almost perfect simplicity and uniformity, all the rich and complex structures of our universe were gradually born. It is a story of cooling, of expansion, of the patient and relentless work of gravity. It is a story that is written in the light of the distant stars, in the composition of the elements, and in the faint, ancient glow of the cosmic microwave background. It is a story that has been pieced together through a century of brilliant theoretical insights and painstaking observational discoveries. It is a story that tells us how our universe came to be, but it is a story that still leaves us with the deepest and most profound of all mysteries, the mystery of the why. The existence of our universe, a universe that is teeming with the intricate and beautiful structures of stars, galaxies, and life, is a profound and deeply puzzling fact. When we examine the fundamental physical laws and constants that govern our cosmos, we find that they appear to be exquisitely and almost miraculously fine-tuned for the emergence of complexity and consciousness. This is not a matter of philosophical speculation. It is a hard, quantitative conclusion drawn from our best and most precise scientific theories. The values of the fundamental constants of nature, the strength of gravity, the charge of the electron, the mass of the proton seem to fall within an incredibly narrow and seemingly arbitrary range of life-permitting values. If any of these numbers were even slightly different, the universe would have been a sterile, barren, and lifeless place. It is as if we have stumbled upon a cosmic recipe that has been calibrated with an almost impossible degree of precision. The initial expansion rate of the universe, for example, is a testament to this delicate balance. If the universe had expanded just a tiny fraction faster in its first second, matter would have been flung apart so quickly that gravity would never have had a chance to pull it together to form the stars and galaxies we see today. The universe would have remained a thin, diffuse, and featureless gas. If it had expanded just a tiny fraction slower, gravity would have quickly overwhelmed the expansion, causing the universe to recollapse into a big crunch long before any complex structures, let alone life, could have had time to form. The observed rate of expansion is balanced on a razor's edge, a perfect and seemingly improbable compromise that allows for a universe that is both long-lived enough and structured enough to support the slow, patient evolution of complexity. The fundamental forces of nature, the four pillars upon which our physical reality is built, also exhibit a remarkable and life-giving fine-tuning. The strong nuclear force, the powerful glue that binds protons and neutrons together in atomic nuclei, is a prime example. If it were just a few percent weaker, the electromagnetic repulsion between protons would tear apart any nucleus with more than one proton. The only element in the universe would be hydrogen. There would be no carbon, no oxygen, no iron, no chemistry, and no life. If it were a few percent stronger, the consequences would be equally catastrophic. Protons would bind together so readily that all the hydrogen in the early universe would have been quickly consumed in nuclear reactions, leaving no fuel for the long-lived, stable stars, like our Sun, that provide the gentle, consistent energy needed for life to evolve. The precise strength of the strong force is a cosmic sweet spot, a perfect balance that allows for a rich and diverse periodic table of the elements. The balance between the forces is also crucial. The electromagnetic force is about 10 to the power of 40 times stronger than the force of gravity. This immense discrepancy is essential. If gravity were much stronger, stars would be smaller, hotter, and would burn out in a geological instant. If it were much weaker, stars and galaxies would never have formed at all. The observed balance allows for gravity to dominate on the large cosmic scales, sculpting the galaxies and the cosmic web, while electromagnetism dominates on the small atomic scales, orchestrating the intricate dance of chemistry and life. The masses of the fundamental particles are another area of exquisite fine-tuning. A free neutron is slightly more massive than a proton, which allows it to decay into a proton, an electron, and an antineutrino. If the proton were slightly more massive than the neutron, it would be the proton that was unstable, and all the protons in the early universe would have decayed into neutrons. There would be no hydrogen, no stars, no water, no us. The tiny and seemingly arbitrary mass difference between these two fundamental particles is a prerequisite for our very existence. Perhaps the most celebrated and most astonishing example of fine-tuning is found in the heart of stars, in the process of stellar nucleosynthesis. All of the carbon in the universe, the very backbone of life, is forged in the cores of stars through a process called the triple alpha process, where 3 helium nuclei fuse together. This process is incredibly difficult, and it is only possible because of a miraculous coincidence in the energy levels of atomic nuclei. The British astronomer Sir Fred Hoyle in the 1950s realized that the observed abundance of carbon in the universe could not be explained by the known nuclear physics of his time. He predicted that there must be a previously unknown resonant energy level in the carbon-12 nucleus, an excited state that had just the right energy to dramatically increase the rate of the triple alpha process. He went to his experimentalist colleagues and implored them to look for this resonance, and to their astonishment, they found it, exactly where Hoyle had predicted it would be, without this specific and seemingly coincidental. Hoyle stated, almost no carbon would be produced in the universe, but the story does not end there. The next step in stellar nucleosynthesis is the fusion of a carbon nucleus with another helium nucleus to form oxygen. If there were a similar resonance in the oxygen nucleus, then all the newly formed carbon would be quickly converted into oxygen, leaving none for the formation of life. As it turns out, the relevant energy level in the oxygen nucleus is just slightly off resonance, which allows for the production of both carbon and oxygen in roughly comparable amounts, the two most essential elements for life after hydrogen and helium. The universe seems to have been built on a series of these incredible, life-giving coincidences. The cosmological constant, the energy of empty space, is perhaps the most extreme example of all. Our best theories predict a value that is 120 orders of magnitude larger than what we observe. If it were this large, the universe would have been torn apart. The fact that it is so incredibly, exquisitely small is a profound and completely unexplained mystery. All of these examples, and many more, point to a universe that appears to be a setup, a put-up job, a place that is not just a random collection of physical laws and constants, but a finely tuned and beautifully coherent system that is, against all odds, perfectly suited for the emergence of complexity, and of beings like us who can marvel at its perfection. The universe we inhabit is a realm of profound and often bewildering contrasts. At the macroscopic level, the world of our everyday experience, things seem to be governed by the deterministic and intuitive laws of classical physics. A ball, when thrown, follows a predictable, parabolic path. The planets orbit the sun in a majestic, clockwork dance. Cause and effect are linked in a clear and unambiguous chain. But as we zoom in, as we probe the microscopic realm of atoms and subatomic particles, this classical common-sense picture dissolves into a reality that is fundamentally probabilistic, interconnected, and deeply strange. This is the world of quantum mechanics, a theory that has been stunningly successful in its predictions, but which continues to challenge our deepest intuitions about the nature of reality. One of the central and most bizarre features of this quantum world is the principle of superposition. In the classical world, an object can only be in one state at a time. A coin is either heads or tails. A cat is either alive or dead. But in the quantum world, a particle, as long as it is not being measured or observed, can exist in a superposition of multiple, mutually exclusive states simultaneously. An electron can be in a superposition of being in many different places at once. An atom can be in a superposition of having both decayed and not decayed. It is not that we simply do not know the particle's true state. The particle's true state is this ghostly to probabilistic blend of all possible states. This is a concept that is famously and absurdly illustrated by the thought experiment of Schrödinger's cat, a creature that is, until the moment of observation, both alive and dead at the same time. This strange superpositional nature of reality has been confirmed by countless experiments, most famously the double-slit experiment, where a single particle seems to pass through two slits at once, behaving like a wave and interfering with itself. Another cornerstone of quantum weirdness is wave-particle duality. Our classical intuition tells us that something is either a discrete, localized particle, like a grain of sand, or a continuous, spread-out wave, like a ripple on a pond. But quantum mechanics tells us that the fundamental constituents of our universe are both light, electrons, and even entire atoms can exhibit both wave-like properties, like interference and diffraction, and particle-like properties, like having a definite position when measured. Their nature is not a fixed, intrinsic property, but is dependent on the context of the experiment, on the question we ask of them. The act of observation seems to be what forces the quantum object to choose which of its dual natures to reveal. This leads to the observer effect, the strange and profound idea that the act of measuring a quantum system is not a passive act of discovering a pre-existing reality, but is an active process that helps to create that reality. The wave function, the mathematical object that describes the superpositional state of a quantum system, is said to collapse upon measurement, with one of the many possibilities being actualized. The nature of this collapse and the role of the observer remains one of the deepest and most unresolved mysteries in all of science. Furthermore, the quantum world is a world of quantization. Many physical properties, like the energy of an electron in an atom, are not continuous, but can only take on certain, discrete, specific values. An electron cannot have just any old energy. It must occupy one of a set of allowed energy levels. When it jumps from a higher level to a lower one, it emits a discrete packet, or quantum, of light, a photon. with a specific energy and color. This is the reason for the sharp, distinct spectral lines we see when we analyze the light from stars. And it is the fundamental reason that atoms are stable. The Heisenberg uncertainty principle adds another layer of profound strangeness. It is a fundamental, built-in limit to our knowledge. It states that there are certain pairs of properties, like a particle's position and its momentum, that cannot both be known with perfect precision at the same time. The more accurately you measure one, the less accurately you can know the other. This is not a limitation of our technology. It is an intrinsic feature of the wave-like nature of reality. It means that the universe, at its core, is not a deterministic, clockwork machine, but a place of inherent, irreducible fuzziness and probability. And perhaps the most spooky of all quantum phenomena is entanglement. Two or more particles can become linked in such a way that their fates are intertwined. No matter how far apart they are separated, a measurement on one particle can instantly influence the state of the other, in a way that seems to defy the cosmic speed limit, the speed of light. This spooky action at a distance, as Einstein called it, has been experimentally confirmed time and time again. And it points to a deep, non-local, and holistic interconnectedness at the very heart of reality. The universe is not a collection of separate, independent things. It is a single, vast, and mysterious quantum system. These strange and beautiful quantum rules are not just an esoteric curiosity for physicists. They are the very foundation upon which our world is built. Without the stability of atoms, guaranteed by quantization, there would be no matter. Without the intricate dance of chemical bonds, governed by the electromagnetic force and quantum mechanics, there would be no complex molecules, no chemistry, no life. The weirdness of the quantum world is not a bug. It is a feature. It is an essential part of the perfect and often paradoxical recipe that allows for the existence of a complex, structured, and conscious universe. The observer effect in quantum mechanics, the strange and profound idea that the act of measurement helps to shape the reality being measured, is one of the most debated and philosophically challenging aspects of modern physics. It is a concept that seems to blur the line between the objective, external world and the subjective, internal world of the observer. This is not just a matter of a clumsy measurement disturbing the system, like trying to measure the temperature of a cup of tea with a large, cold thermometer. It is a more fundamental and more mysterious process. At its core lies the collapse of the wave function. A quantum system, before it is measured, exists in a superposition of all its possible states, a ghostly cloud of potential described by the wave function. The act of measurement seems to force this cloud of possibilities to collapse into a single, definite, actualized state. But what precisely constitutes a measurement? Where does the strange, probabilistic world of quantum mechanics end, and the familiar, definite world of our classical experience begin? This is the measurement problem. And it is a deep, unresolved wound at the heart of the theory. The traditional Copenhagen interpretation of quantum mechanics, developed by Niels Bohr and Werner Heisenberg, takes a pragmatic but philosophically cautious approach. It simply posits a fundamental divide, a shifty split, between the quantum world of microscopic systems and the classical world of our macroscopic measuring devices. When a quantum system interacts with a classical measuring device, the collapse just happens. The theory does not explain the mechanism of this collapse. It treats it as a fundamental and unexplained feature of nature. This is a deeply unsatisfying answer for many, as it leaves the boundary between the quantum and classical worlds ill-defined, and elevates measurement to a special, almost mystical status. In response to this, other interpretations have been proposed. The many worlds interpretation, first conceived by Hugh Everett III in 1957, offers a radical and elegant solution: the wave function never collapses. The smooth, continuous evolution of the wave function, as described by the Schrödinger equation, is the only process that ever occurs when a measurement is made. The universe itself splits, or branches, into multiple parallel realities, one for each possible outcome. In one universe, the electron is detected at the top of the screen. In another, it is detected at the bottom. The observer also splits, with different versions of the observer experiencing different outcomes. In this view, reality is a constantly branching tree of possibilities, and we are just following one particular path through this vast multiverse. There is no special measurement process, no mysterious collapse, only the universal, deterministic evolution of the wave function of the whole cosmos. Another approach is the de Broglie-Bohm theory, or pilot wave theory. This interpretation posits that particles, like electrons, always have a definite, if unknown, position. They are real, objective entities, but they are guided in their motion by a pilot wave, a real physical wave that is described by the wave function. In the double-slit experiment, the pilot wave passes through both slits and creates an interference pattern, which then guides the particle to land in one of the bright bands on the screen. This restores a sense of objective, deterministic reality. But it does so at the cost of introducing a profound non-locality. The pilot wave is a holistic entity that can be influenced by events happening anywhere in the universe, instantaneously. A third class of theories, known as spontaneous collapse or objective collapse models, proposes that the collapse is a real physical process that happens randomly and spontaneously, independent of any observer. The collapse is a fundamental, new law of nature, a slight modification to the Schrödinger equation. For a single, isolated particle, the chance of a spontaneous collapse is incredibly small, so it can maintain its superposition for a long time. But for a macroscopic object, which consists of a vast number of entangled particles, the probability of a collapse occurring in one of its constituent particles becomes overwhelmingly high, triggering a rapid chain reaction collapse of the entire system. This is why we never see macroscopic objects like cats in a superposition. They are simply too large and complex to maintain their quantum coherence. Schrödinger's cat, the famous thought experiment that so beautifully illustrates the paradox of the measurement problem, is a powerful reminder of the deep conceptual chasm that separates the quantum and classical worlds. The cat in the box, suspended in its ghostly state between life and death, is a metaphor for the profound weirdness that ensues when we try to apply the rules of the micro-world to the world of our everyday experience, and the mystery is deepened still further by the quantum eraser experiment. This is a clever and subtle variation of the double-slit experiment, which shows that the past behavior of a quantum particle can be influenced by a choice made in the future. In this experiment, which path information is recorded, which destroys the interference pattern. But if this information is later erased in a way that makes it impossible to know which path the particle took, the interference pattern can be made to reappear, even if the erasure happens long after the particle has hit the detector screen. This suggests that the relationship between past, present, and future, between cause and effect, is far more subtle and interconnected in the quantum world than our classical intuition would ever allow. The observer effect, in all its strange and paradoxical glory, is not just a curiosity for physicists. It is a profound and fundamental challenge to our classical worldview. A challenge that suggests that reality may be a far more fluid, more interconnected, and more participatory process than we ever imagined. The unidirectional flow of time, the arrow of time, is one of the most fundamental and yet most mysterious aspects of our experience. We are born, we live, we die. We remember the past, but not the future. Cause always precedes effect. This seems so obvious, so deeply ingrained in the fabric of our reality, that we rarely stop to question it. But when we look at the most fundamental laws of physics, this arrow of time is nowhere to be found. The laws of Newtonian mechanics, of electromagnetism, of relativity, and even of quantum mechanics are all, with one minor exception related to the weak nuclear force, time-symmetric. They work just as well for a movie played forwards as for a movie played backwards. If you were to watch a video of individual atoms colliding, you often could not tell if the video was playing forwards or in reverse. The laws governing these tiny interactions do not inherently distinguish between past and future. So, if the microscopic laws are time-symmetric, why does time have such a clear and undeniable direction in our macroscopic world? The answer lies primarily in the second law of thermodynamics and the concept of entropy. Entropy is a measure of disorder, randomness, or the number of possible microscopic arrangements of particles in a system. The second law of thermodynamics states that the total entropy of an isolated system can only increase over time or remain constant, but it can never decrease. This law is not a fundamental law like gravity or electromagnetism. Rather, it is a statistical law. It is overwhelmingly probable that systems will evolve from states of lower entropy to states of higher entropy, simply because there are vastly more ways for a system to be disordered than ordered. Consider everyday examples. If you drop a glass, it shatters into many pieces. This is an increase in entropy, moving from an ordered state to a disordered state. It is theoretically possible for the pieces to spontaneously reassemble, but the probability of all the atoms and molecules in the glass randomly moving in precisely the right way at the same time to reconstruct the original glass is astronomically small, effectively zero. Similarly, a lump of sugar dissolves in coffee, spreading its molecules throughout the liquid. The reverse process, the sugar molecules spontaneously recollecting into a lump at the bottom of the cup, never happens. Heat always flows from a hot object to a cold object, never the other way around, because this process increases the overall entropy of the system. These irreversible processes define the thermodynamic arrow of time. The existence of this thermodynamic arrow of time in our universe is deeply connected to its initial state. For entropy to increase, the universe must have started in an incredibly low entropy, highly ordered state. The Big Bang, roughly 13.8 billion years ago, describes a universe that began as an extremely hot, dense, and remarkably uniform plasma. While incredibly hot, this state was also highly ordered in terms of its gravitational configuration. All the matter and energy were concentrated in a tiny volume, with very little gravitational clumping. This initial low entropy provided the room for entropy to increase over cosmic time, driving the evolution of the universe from a smooth, uniform state to one filled with complex structures like stars, galaxies, and life. If the universe had begun in a high-entropy, disordered state, it would have quickly reached a state of thermal equilibrium, where everything is uniformly distributed and nothing interesting happens. There would be no processes, no evolution, and no arrow of time. The origin of this initial low entropy is itself a profound cosmological puzzle, often referred to as the past hypothesis. Why did the Big Bang start with such incredible order? Beyond the thermodynamic arrow, there are other arrows of time that are ultimately linked to it. The cosmological arrow of time refers to the universe's continuous expansion. As the universe expands, its volume increases. Matter and energy become more diffuse, and its overall entropy increases. This expansion provides a cosmic direction for time. If the universe were to eventually contract in a hypothetical Big Crunch, then the cosmological arrow would reverse, and entropy might decrease in that phase. but our current observations indicate an accelerating expansion. The radiative arrow of time refers to the fact that electromagnetic waves, such as light, always propagate outwards from their source, never converging inwards to a source. A light bulb emits light that spreads out. It does not absorb light from space to become brighter. This is also fundamentally connected to the second law of thermodynamics, as an inward converging wave would represent a highly ordered, low-entropy state that is statistically improbable to occur spontaneously. Finally, there is the psychological arrow of time, which is our subjective experience of time flowing from past to future. We remember the past, not the future. Our brains are structured to record information from past events, and our actions are aimed at influencing future outcomes. This psychological arrow is almost certainly a consequence of the thermodynamic arrow. The processes of memory formation, learning, and consciousness itself involve increasing the entropy of our brains and their environment. We build memories by creating ordered structures from disordered inputs, but the overall process of living and interacting with the world increases total entropy. The arrow of time is not just an abstract concept. It is what makes the universe dynamic and interesting. It allows for the formation of complex structures, from atoms to galaxies, and for the emergence of life and consciousness. It dictates that cause precedes effect, enabling predictable processes and the very possibility of scientific inquiry. Without the arrow of time, the universe would be a static, unchanging, or randomly fluctuating mess, devoid of the evolution, history, and complexity that define our existence. The fact that time flows in one direction, driven by the relentless march towards increasing disorder, is a fundamental property of our universe that enables everything we perceive and experience. The universe, in its fundamental design, appears to be a place of astonishing precision, almost as if it were calibrated with exquisite care for the emergence of complexity and life. This observation is often referred to as the concept of cosmic coincidences, or fine-tuning. It highlights that numerous fundamental physical constants and initial conditions of the universe possess values that fall within an incredibly narrow range, such that if they were even slightly different, the universe would be profoundly inhospitable to stars, galaxies, chemistry, and ultimately, life as we know it. These are not merely fortunate accidents. They represent a series of highly specific parameters in a vast landscape of possibilities, making the existence of our universe seem remarkably improbable. One of the most striking examples of fine-tuning involves the strength of the strong nuclear force. This force, which binds protons and neutrons together to form atomic nuclei, is immensely powerful but acts only over incredibly short distances. If the strong force were just a few percent weaker, atomic nuclei beyond hydrogen would be unstable. Protons would repel each other too strongly due to the electromagnetic force, preventing the formation of elements like carbon, oxygen, and nitrogen, which are the building blocks of life. The universe would be a monotonous expanse of hydrogen and perhaps some helium. Conversely, if the strong force were just a few percent stronger, protons might bind too readily, perhaps forming stable diprotons or other exotic nuclei that would consume all hydrogen in the early universe. This would mean no water, no long-lived stars like our Sun, and a drastically different, likely lifeless, cosmos. The observed strength allows for a diverse range of stable elements and long-lived stars. The mass difference between a proton and a neutron is another crucial cosmic coincidence. A neutron is slightly more massive than a proton. This tiny mass difference, approximately 0.13% of the proton's mass, is vital. If the neutron were even slightly lighter than the proton, all protons in the early universe would have converted into neutrons. This would lead to a universe with no hydrogen, and thus no water, no long-lived stars, and a very different chemistry. If the neutron was significantly heavier, it would have decayed too quickly into a proton before Big Bang nucleosynthesis could produce sufficient helium. The precise mass difference ensures the right balance of protons and neutrons in the early universe, allowing for the formation of hydrogen and helium in the correct proportions, which are essential for stellar evolution and the subsequent creation of heavier elements. The strength of the electromagnetic force relative to the strong force and gravity is also finely tuned. Electromagnetism dictates how electrons orbit atomic nuclei and how atoms form molecules. If it were much stronger, electrons would be pulled too tightly to nuclei, preventing the formation of complex molecules. If it were much weaker, electrons might not form stable orbits, or atoms would be too diffuse. Furthermore, the ratio of the electromagnetic force to gravity is enormous, approximately 10 to the power of 40. This vast difference is essential. Gravity dominates on large scales, forming stars and galaxies, while electromagnetism dominates on atomic scales, allowing for chemistry. If gravity were much stronger relative to electromagnetism, stars would burn out too quickly, or the universe would be dominated by black holes. If electromagnetism were much weaker, matter might not clump into stars and galaxies effectively. Perhaps one of the most celebrated and most astonishing examples of fine-tuning involves the energy levels within carbon and oxygen atomic nuclei, particularly the Hoyle resonance. Carbon, with its 6 protons, is the backbone of all known life. It is primarily produced in the cores of stars when 3 helium nuclei fuse together. This triple alpha process is inherently difficult because the intermediate step, the fusion of 2 helium nuclei, forms an unstable beryllium-8 nucleus that quickly decays. For carbon-12 to form in sufficient quantities, there must be a specific energy level, or resonance, in the carbon-12 nucleus that precisely matches the energy of the fusing helium and beryllium nuclei. Sir Fred Hoyle, a British astronomer, predicted this resonance in the 1950s, arguing that its existence was necessary for carbon to be produced in the universe. Without this precise resonance, virtually no carbon would form, making carbon-based life impossible. Similarly, the energy level of oxygen-16 is also critical. It allows oxygen to form from carbon and helium, but it is just slightly off resonance enough to prevent all carbon from being converted into oxygen. This delicate balance ensures the cosmic abundance of both carbon and oxygen, the 2 most vital elements for life after hydrogen and helium. The cosmological constant, which represents the energy density of empty space, is another parameter exhibiting extreme fine-tuning. Its observed value is incredibly small, yet positive, by a factor of approximately 120 orders of magnitude smaller than theoretical predictions from quantum field theory. If the cosmological constant was significantly larger, its repulsive force would have caused the universe to expand so rapidly that matter could never have clumped together to form galaxies, stars, or any stable structures. The universe would have been a desolate, rapidly expanding void. If it were negative and too large, the universe would have collapsed back on itself almost immediately. The fact that its value is so tiny, allowing for both structure formation and accelerated expansion over billions of years, is a profound cosmic coincidence. Even the number of spatial dimensions we inhabit, 3, appears to be finely tuned for complexity. In a universe with only 2 spatial dimensions, complex structures like nervous systems or circulatory systems, which require intricate interconnections without crossing paths, would be difficult or impossible to form. Stable planetary orbits around stars are also problematic in 2 dimensions. In a universe with 4 or more spatial dimensions, the inverse square law of gravity would change, becoming an inverse cube law in 4 dimensions. For instance, this would cause planetary orbits to be unstable, spiraling inward or outward, and would likely prevent the formation of stable atoms, as electrons would not maintain stable orbits around nuclei. The existence of precisely 3 spatial dimensions seems essential for the kind of complex, stable structures that underpin life. Faced with the astonishing array of cosmic coincidences and the apparent fine-tuning of the universe's fundamental constants and initial conditions, scientists and philosophers have developed various interpretations. One of the most prominent is the anthropic principle. This principle, in its various forms, offers a way to understand why the universe appears to be so exquisitely suited for life, not by invoking a designer, but by considering the necessary conditions for the existence of observers like ourselves. It essentially turns the question around, rather than asking why the universe is fine-tuned. It asks what kind of universe we must inhabit, given that we exist to observe it. The most widely accepted and least controversial version is the weak anthropic principle. This principle states that the observed values of all physical and cosmological quantities are not equally probable, but take on values restricted by the requirement that there exist places where carbon-based life can evolve, and by the requirement that the universe be old enough for it to have already done so. In simpler terms, the WAP is a selection effect. If there were many universes or many regions within a single, vastly larger universe, each with different physical laws or different values for fundamental constants, then only those universes or regions that allow for the formation of stars, planets, and complex chemistry would be capable of hosting life. We, as observers, necessarily find ourselves in one of these life-permitting universes or regions. It is like finding yourself on a habitable planet with liquid water and a breathable atmosphere. You wouldn't find yourself on a barren, airless rock. So, observing a habitable planet is not surprising. It's a prerequisite for your presence. The WAP does not explain why the universe is fine-tuned, but rather explains why we observe it to be fine-tuned. It is a statement about our observational bias. The WAP gains significant explanatory power when combined with the multiverse hypothesis. If our universe is not the only one, but merely one among an enormous, perhaps infinite, ensemble of universes, then the apparent fine-tuning becomes less miraculous. In a multiverse, each universe could have different physical laws, different fundamental constants, and different initial conditions. In such a scenario, it is statistically inevitable that some universes would happen to have the precise combination of parameters necessary for the emergence of life. Our universe would simply be one of those rare, fortunate ones. We exist here because this is one of the few places where we could exist. The multiverse thus provides a framework for the WAP to function as a plausible scientific explanation for fine-tuning, shifting the question from why is this universe fine-tuned to how did the multiverse generate so many variations. Different theoretical models propose various types of multiverses. One prominent idea is the inflationary multiverse, arising from the theory of cosmic inflation. If inflation, the rapid expansion in the very early universe, is eternal, it could continuously spawn new bubble universes or pocket universes. Each of these bubbles could potentially have different physical laws and constants depending on how the scalar field driving inflation settles down. Another concept comes from string theory, which suggests that our universe exists on a brane within a higher dimensional space. String theory also predicts a vast landscape of possible vacuum states, each corresponding to a different set of physical laws and constants. If all these states are realized in different universes, then the fine-tuning of our universe could be explained by our selection bias within this landscape. A more controversial version is the strong anthropic principle. This principle states that the universe must have those properties which allow life to develop within it at some stage. This goes beyond mere observation and implies a deeper necessity or compulsion for the universe to be life-permitting. It suggests that the laws of physics are not just randomly chosen, but are somehow compelled to be life-permitting. Some interpretations of the SAP verge into teleological or even theological territory, implying that the universe was somehow designed or destined for life. However, most scientific discussions of the SAP interpret it as a stronger form of the WAP, suggesting that the very existence of fundamental laws or the initial conditions of the universe are such that they must lead to observers. The anthropic principle, particularly the multiverse interpretation, faces several criticisms. One major critique is its lack of empirical testability. If other universes exist, they are, by definition, beyond our observable horizon and cannot be directly accessed or measured. This makes the multiverse hypothesis difficult to falsify or verify through traditional scientific methods, leading some to argue that it falls outside the realm of science. Another criticism is that it shifts the problem of fine-tuning rather than solving it. If our universe is fine-tuned, then what about the multiverse itself? Is the multiverse fine-tuned to produce universes like ours? This can lead to an infinite regress of explanations. Furthermore, some argue that the anthropic principle is a tautology, a statement that is true by definition and therefore provides no new information. Of course, we must find ourselves in a universe that allows for our existence. This doesn't explain why such a universe exists in the first place. Despite these criticisms, the anthropic principle, especially the weak version combined with the multiverse, offers a compelling framework for addressing the fine-tuning problem without resorting to supernatural explanations. It transforms the apparent improbability of our universe into a statistical inevitability within a larger cosmic landscape, while it may not provide a definitive answer to the ultimate why question. It offers a powerful scientific perspective on why the universe appears to have a perfect recipe for life, by emphasizing the crucial role of observers in selecting the specific reality they inhabit. It forces us to confront the possibility that our universe might be just one of countless others, each a different roll of the cosmic dice. The universe, as observed by astronomers and physicists, appears to be remarkably fine-tuned for the existence of life. Numerous fundamental physical constants, such as the strength of gravity, the mass of the electron, and the initial expansion rate of the cosmos, possess values that fall within an incredibly narrow range. If these values were even slightly different, the universe would be profoundly inhospitable to stars, galaxies, complex chemistry, and ultimately, life as we know it. This apparent cosmic coincidence has led to deep philosophical and scientific questions about why our universe seems to have such a perfect recipe. One of the most compelling and actively discussed theoretical frameworks attempting to address this fine-tuning problem is the multiverse theory. This concept proposes that our universe is not unique, but is merely one of an enormous, perhaps infinite, number of universes, each potentially possessing different physical laws, fundamental constants, and initial conditions. The core idea behind the multiverse is to transform the apparent improbability of our universe's fine-tuning into a statistical inevitability. If there are countless universes, each with a different set of physical parameters, then it becomes statistically probable, even guaranteed, that at least one of these universes would happen to have the precise combination of values necessary for the formation of stars, planets, and the emergence of life. In this scenario, our existence as observers means we necessarily find ourselves in one of these rare, life-permitting universes. This is the essence of the weak anthropic principle, which states that we observe the universe to be fine-tuned because only such a universe could support our existence. The multiverse provides the vast ensemble of possibilities required for the anthropic principle to be a plausible explanation, rather than a mere tautology. The concept of a multiverse arises from various theoretical extensions of our current understanding of physics, rather than being a single, unified theory. One prominent source of multiverse ideas stems from cosmic inflation, a widely accepted theory describing an extremely rapid, exponential expansion of the universe in its earliest moments. While standard inflation explains many features of our universe, such as its flatness and uniformity, some models of inflation, particularly those involving a scalar field that drives the expansion, suggest that inflation might not end everywhere simultaneously. Instead, quantum fluctuations in this field could cause inflation to stop in certain localized regions, forming bubbles of space-time that become individual universes, while in other regions, inflation continues indefinitely, spawning new bubbles. This leads to the idea of eternal inflation, where an infinitely branching, self-reproducing, inflationary space-time continuously generates new universes. Each of these bubble universes, once formed, is essentially a separate Big Bang event. From the perspective of an observer inside one of these bubbles, their universe would appear to have originated from a singular point and expanded, just like our own. However, from the perspective of the larger, eternally inflating space-time, these bubbles are constantly being created and expanding within a larger, non-ending inflationary background. A key feature of these bubble universes is that they can possess different physical properties. The way the inflaton field decays and settles into a stable vacuum state can vary from one bubble to another. Each vacuum state corresponds to a different set of fundamental physical laws and constants. For example, in one bubble universe, the strength of gravity might be slightly different. In another, the mass of the electron might be larger, or the cosmological constant might have a different value. Some bubble universes might even have a different number of effective spatial dimensions or different types of fundamental particles. This vast diversity of properties across the ensemble of bubble universes is what makes the eternal inflation model a powerful candidate for explaining the fine-tuning of our own universe. If there are an infinite number of such bubbles, each with a random assortment of physical laws, then it is statistically inevitable that some of them will happen to have the precise combination of parameters necessary for the formation of stars, galaxies, chemistry, and ultimately, life. We, as observers, necessarily find ourselves in one of these rare, life-permitting bubbles. Another theoretical avenue for the multiverse comes from string theory and its extension, M-theory. String theory attempts to unify all fundamental forces and particles by proposing that the most basic constituents of reality are not point-like particles, but tiny, one-dimensional, vibrating strings, unimaginably small. Different vibration modes of these strings correspond to different fundamental particles and forces. A key feature of string theory is that it requires the existence of more than the familiar 4 space-time dimensions. For the theory to be mathematically consistent, it often predicts 10 or 11 space-time dimensions. The reason we only perceive 4 dimensions is that the extra dimensions are thought to be compactified, or curled up into incredibly tiny, unobservable spaces. The way these extra dimensions are curled up, known as the Calabi-Yau manifold, can vary in an enormous number of ways, estimated to be as high as 10 to the power of 500 different possible geometries. Each of these geometries would correspond to a different set of physical laws and fundamental constants in the 4 large dimensions we experience. This vast number of possibilities is often referred to as the landscape of string theory. If each point in this landscape represents a different universe, then the universe we inhabit is simply one of the countless possibilities within this string landscape. The implications of a multiverse are profound. Firstly, it offers a purely naturalistic explanation for the universe's fine-tuning, reducing the need to invoke supernatural or teleological explanations. If there are infinite rolls of the cosmic dice, then it is no longer a miracle that one particular roll came up with the winning numbers for life. Secondly, it challenges the traditional view of our universe as the entirety of existence. Our observable universe, vast as it is, might just be a tiny speck within a much larger, incomprehensibly immense multiverse. Thirdly, it raises new questions about the origin and nature of the multiverse itself. If our universe requires an explanation for its existence, does the multiverse also require one? This can lead to an infinite regress of explanations, or suggest that the multiverse is a brute fact that simply exists without further cause. However, the multiverse theory also faces significant challenges and criticisms. The most prominent challenge is its lack of direct empirical testability. By definition, other universes in many multiverse models are causally disconnected from our own, meaning we cannot send signals to them, observe them directly, or interact with them. This makes it incredibly difficult, if not impossible, to gather direct observational evidence to confirm or refute their existence through traditional scientific methods. Some physicists argue that this lack of testability places the multiverse hypothesis outside the realm of empirical science, relegating it to philosophy or metaphysics. Proponents, however, argue that while direct observation might be impossible, indirect evidence could emerge, such as specific patterns in the cosmic microwave background radiation that might hint at collisions with other universes, or the discovery of new particles predicted by theories that also lead to a multiverse. Another challenge is the measure problem in infinite multiverses. If there are an infinite number of universes, how do we assign probabilities to different outcomes or properties? If every possible universe exists an infinite number of times, then any specific event, no matter how improbable, occurs infinitely often. This makes it difficult to make predictions or test the theory, as any outcome could be explained by some universe existing. Despite these challenges, the multiverse theory remains a powerful and elegant conceptual framework for addressing some of the deepest puzzles in cosmology, particularly the apparent fine-tuning of our universe, by embedding our reality within a much grander and more diverse cosmic tapestry. The concept of bubble universes emerges primarily from the theory of cosmic inflation, a cornerstone of modern cosmology that describes an extremely rapid, exponential expansion of the universe in its earliest moments. While the standard Big Bang model explains the universe's evolution from a hot, dense state, it faced several puzzles, such as the flatness problem, the horizon problem, and the monopole problem. Cosmic inflation, proposed in the 1980s, elegantly solves these problems by positing a brief but incredibly powerful burst of expansion. During inflation, which is thought to have occurred between approximately 10 to the power of minus 36 and 10 to the power of minus 32 seconds after the Big Bang, the universe expanded by an enormous factor, perhaps as much as 10 to the power of 26 or more. This rapid stretching smoothed out any initial irregularities, making the universe flat and uniform on large scales. The energy driving this expansion is typically attributed to a hypothetical scalar field, often called the inflaton field. This field possessed a high energy density that acted as a repulsive gravitational force, pushing space-time apart at an accelerating rate. At the end of inflation, the inflaton field decayed, converting its energy into the hot, dense soup of particles and radiation that constituted the initial conditions for the standard Big Bang expansion. The idea of bubble universes arises when we consider the possibility of eternal inflation. In many models of inflation, the inflaton field does not decay uniformly or simultaneously across all of space-time. Instead, quantum fluctuations within the inflaton field can cause inflation to stop in certain localized regions, while in other regions, the field continues to fluctuate and drive inflation. When inflation stops in a particular region, that region reheats and becomes a distinct bubble universe that begins to expand and evolve according to the standard Big Bang model. However, the surrounding space continues to inflate, creating new regions where inflation can end, thus spawning more bubble universes. This process can continue indefinitely, leading to an infinitely branching, self-reproducing, inflationary space-time, a multiverse composed of an endless number of these causally disconnected bubble universes. Each of these bubble universes, once formed, is essentially a separate Big Bang event. From the perspective of an observer inside one of these bubbles, their universe would appear to have originated from a singular point and expanded, just like our own. However, from the perspective of the larger, eternally inflating space-time, these bubbles are constantly being created and expanding within a larger, non-ending inflationary background. A key feature of these bubble universes is that they can possess different physical properties. The way the inflaton field decays and settles into a stable vacuum state can vary from one bubble to another. Each vacuum state corresponds to a different set of fundamental physical laws and constants. For example, in one bubble universe, the strength of gravity might be slightly different. In another, the mass of the electron might be larger, or the cosmological constant might have a different value. Some bubble universes might even have a different number of effective spatial dimensions or different types of fundamental particles. This vast diversity of properties across the ensemble of bubble universes is what makes the eternal inflation model a powerful candidate for explaining the fine-tuning of our own universe. If there are an infinite number of such bubbles, each with a random assortment of physical laws, then it is statistically inevitable that some of them will happen to have the precise combination of parameters necessary for the formation of stars, galaxies, chemistry, and ultimately, life. We, as observers, necessarily find ourselves in one of these rare, life-permitting bubbles. The scale of these bubble universes is immense. Each individual bubble can be unimaginably vast, perhaps even infinite in extent, and they are separated from each other by regions of still inflating space, which expands so rapidly that it prevents any interaction or communication between the bubbles. This means that even if another bubble universe were to collide with ours, we would likely never know it, as the event would occur in a region of space-time that is receding from us faster than the speed of light. While the concept of bubble universes arising from eternal inflation is a highly theoretical one, it emerges naturally from the mathematical framework of inflationary cosmology, which is widely accepted for its ability to solve the problems of the standard Big Bang model. It provides a compelling, naturalistic explanation for the apparent fine-tuning of our universe without resorting to a designer. However, it also presents significant challenges. The lack of direct observational evidence for other bubble universes remains a major hurdle, as their causal disconnection makes them inherently unobservable. Furthermore, the measure problem in infinite multiverses, which deals with how to assign probabilities to different outcomes in an infinite ensemble, remains an active area of research and debate. Despite these challenges, the idea of bubble universes offers a fascinating and powerful perspective on the origin and nature of our cosmos, suggesting that our universe might be just one tiny, habitable pocket within an infinitely larger, eternally expanding cosmic foam. The hypothesis that our universe and everything within it is in fact a highly sophisticated computer simulation is a fascinating and profoundly unsettling idea that challenges our fundamental understanding of reality. This concept, often explored in science fiction, has gained traction in philosophical and scientific circles, primarily driven by arguments about the potential capabilities of future advanced civilizations. It suggests that our perceived reality is not a fundamental, base reality, but rather an artificial construct, much like a virtual reality game, designed and run by a more technologically advanced civilization existing in a higher-level reality. The most compelling argument for the simulation hypothesis was put forth by the philosopher Nick Bostrom in 2003. His argument is based on a probabilistic trilemma. At least one of three propositions must be true. First, that civilizations almost never reach a post-human stage capable of running highly realistic simulations. This could be due to self-destruction, technological stagnation, or some other limiting factor. Second, that post-human civilizations, if they do arise, almost never run a significant number of ancestor simulations. This implies they might have no interest in simulating their past. Or they might consider it unethical. Or they might simply prefer other forms of entertainment or research. Third, that we are almost certainly living in a simulation. If post-human civilizations are common, and if they are interested in running ancestor simulations, then the number of simulated realities would vastly outnumber the single, base reality. Therefore, statistically, it would be far more probable that we exist within one of these many simulations, rather than in the single, original reality. The argument relies on the assumption that the technological capacity to create highly realistic, conscious agent-filled simulations is achievable. Given the rapid advancements in computing power observed over the past decades, such a future seems plausible, at least conceptually. If our own civilization continues to advance at its current pace, it is conceivable that within centuries or millennia, we might possess the computational resources to simulate entire universes or historical periods with conscious beings. If we can, then it stands to reason that other, older, more advanced civilizations could already be doing so. While the simulation hypothesis is primarily a philosophical argument, some proponents point to certain features of our universe that, while not definitive proof, could be interpreted as evidence or glitches consistent with a simulated reality. One such feature is the fine-tuning of the universe's fundamental constants. As discussed in previous chapters, the precise values of gravity, electromagnetism, particle masses, and the cosmological constant seem perfectly calibrated for life. In a simulated universe, these parameters could simply be the settings chosen by the simulators to create a particular kind of environment or to achieve specific outcomes. This would explain the fine-tuning without resorting to chance or a divine creator. Another intriguing aspect is the quantum nature of reality. The probabilistic behavior of particles, the wave-particle duality, and the observer effect could be interpreted as computational optimizations. In a simulation, rendering every single particle in the universe at all times would be computationally expensive. Instead, the simulation might only render or compute the state of a particle when it is observed or interacted with. Much like a video game only renders the parts of the environment visible to the player. The inherent discreteness of reality at the Planck scale, the smallest possible units of length and time, could also be seen as the pixelation or computational resolution limit of the simulation. The mathematical nature of physical laws is also cited. The universe operates according to elegant and precise mathematical equations. This could simply be a reflection of its underlying computational code. Conservation laws, such as the conservation of energy and momentum, could be built-in rules of the simulation to ensure consistency. The finite speed of light could be a computational constraint, a maximum processing speed within the simulated environment. The Fermi paradox, which questions why we haven't detected any evidence of alien civilizations despite the high probability of their existence, could also be explained by the simulation hypothesis. Perhaps our simulation is limited to our observable universe, or other civilizations are simply not simulated within our particular instance. The philosophical implications of living in a simulated reality are profound. It raises questions about the nature of consciousness, free will, and purpose. If our reality is simulated, are our thoughts and emotions truly our own, or are they part of the program? What is the purpose of the simulation? Are we historical ancestors, experimental subjects, or simply entertainment? The identity of the simulators also becomes a question. Are they also simulated? This could lead to an infinite regress of simulations within simulations. However, even if we are simulated, our experiences, emotions, and relationships are real within the simulation. The suffering and joy we experience are not diminished by the fact that our reality might be running on a computer. Proving or disproving the simulation hypothesis is incredibly difficult. Direct evidence is unlikely, as the simulators would presumably make the simulation indistinguishable from base reality. Scientists might look for bugs or glitches in the fabric of reality, computational limits being hit, or subtle anomalies that suggest an artificial construct. However, any such anomaly could also be explained by new, undiscovered physics. Ultimately, the simulation hypothesis remains a powerful thought experiment that forces us to critically examine the nature of our existence and the limits of our perception, pushing the boundaries of what we consider real. The universe, in its profound complexity and underlying order, speaks a language that transcends human spoken words, the language of mathematics, from the smallest subatomic particles to the grandest cosmic structures. The fundamental workings of reality appear to be governed by precise mathematical laws and relationships. This pervasive mathematical nature of the cosmos is not merely a convenient tool for scientists to describe phenomena. It seems to be an intrinsic property of existence itself, leading to deep philosophical questions about why mathematics is so incredibly effective at describing the natural world. For centuries, thinkers have pondered this remarkable connection. Ancient Greek philosophers like Pythagoras believed that numbers held the key to understanding the universe, seeing mathematical ratios in musical harmony and celestial motions. Later, in the 17th century, Galileo Galilei famously asserted that the book of nature is written in the language of mathematics. This insight proved prescient, as the scientific revolution that followed was built upon the foundation of mathematical descriptions of physical reality. Consider Isaac Newton's laws of motion and universal gravitation, formulated in the late 17th century. These laws, expressed as elegant mathematical equations, precisely describe how objects move under the influence of forces and how masses attract each other. Newton's mathematical framework allowed for the accurate prediction of planetary orbits, the trajectory of projectiles, and the behavior of tides, ushering in an era of unprecedented scientific predictability. His work demonstrated that the seemingly chaotic movements of the heavens and the seemingly simple motions on Earth were governed by the same universal mathematical principles. In the 19th century, James Clerk Maxwell unified electricity and magnetism into a single electromagnetic force, again through a set of powerful mathematical equations. Maxwell's equations not only described all known electrical and magnetic phenomena, but also predicted the existence of electromagnetic waves which travel at the speed of light. This mathematical prediction was later confirmed by Heinrich Hertz's experiments in the late 1880s, demonstrating that light itself is an electromagnetic wave. This was a triumph of mathematical reasoning, revealing a deeper unity in nature that was not immediately apparent through observation alone. The 20th century brought even more profound mathematical revelations. Albert Einstein's theories of special and general relativity, developed in the early 1900s, fundamentally reshaped our understanding of space, time, gravity, and energy. These theories are expressed in highly sophisticated mathematical frameworks, particularly differential geometry for general relativity. Einstein's equations describe gravity not as a force, but as the curvature of space-time caused by mass and energy. These equations predicted phenomena such as the bending of light by massive objects, the existence of gravitational waves, and the precise orbital precession of Mercury, all of which have been confirmed with extraordinary accuracy. Similarly, quantum mechanics, the theory describing the behavior of matter and energy at the atomic and subatomic scales, is inherently mathematical. Concepts like wave functions, probability amplitudes, and the quantization of energy are all expressed using advanced mathematical tools, including linear algebra and complex numbers. Quantum mechanics predicts the discrete energy levels of atoms, the behavior of elementary particles, and the outcomes of particle interactions with astonishing precision. Many of its predictions, such as the existence of antimatter and the Higgs boson, were made purely through mathematical reasoning before experimental verification. This consistent success of mathematics in describing and predicting the physical world has led many to ponder its deeper significance. Eugene Wigner, a Nobel laureate in physics, famously wrote about the unreasonable effectiveness of mathematics in the natural sciences in 1960. He marveled at how abstract mathematical concepts, often developed for purely intellectual reasons without any immediate physical application in mind, later turn out to be precisely what is needed to describe fundamental aspects of the universe. For example, group theory, a branch of abstract algebra, found unexpected applications in describing the symmetries of elementary particles and the conservation laws that govern their interactions. Is mathematics invented by the human mind, a useful language we create to categorize and understand the world? Or is it discovered, an inherent structure of reality that exists independently of human consciousness? The remarkable predictive power and universal applicability of mathematics and physics suggests that it might be more than just a human construct. It implies that the universe itself is fundamentally structured in a mathematical way, that its laws are not arbitrary, but follow a deep, elegant, and consistent mathematical logic. The presence of symmetries in nature, which are beautifully described by mathematics, further reinforces this idea. Symmetries in physical laws often correspond to conservation laws. For example, the symmetry of physical laws under translation in time leads to the conservation of energy. Symmetry under translation in space leads to the conservation of momentum. The conservation of angular momentum is linked to the laws being the same regardless of orientation. These deep connections between abstract mathematical symmetries and conserved physical quantities reveal a profound mathematical elegance woven into the fabric of space-time. The universe's adherence to mathematical laws provides a framework for its predictability and order. Without this underlying mathematical structure, the cosmos would be chaotic and unpredictable, making scientific inquiry impossible. The fact that we can formulate theories, make predictions, and consistently verify them through observation and experiment is a testament to the universe's inherent mathematical coherence. This mathematical language is not just a description of what is. It is often a guide to what must be, revealing hidden truths about reality before they are directly observed. It suggests that the universe is not just a collection of random events, but a system built upon a foundation of logical and consistent mathematical principles, making its very existence and its capacity for complexity a profound mathematical marvel. Our everyday experience of the universe is confined to 3 spatial dimensions: length, width, and height, and 1 temporal dimension. Time, we move forward and backward, up and down, left and right, and always forward in time. This 4-dimensional space-time continuum, as described by Albert Einstein's theories of relativity, forms the familiar stage upon which all cosmic events unfold. However, many cutting-edge theories in modern physics propose the existence of additional dimensions beyond these familiar 4. These extra dimensions are not merely speculative concepts. They arise naturally from attempts to unify the fundamental forces of nature and to solve some of the deepest puzzles in physics, such as why gravity is so much weaker than the other forces. The idea of extra dimensions is not new. In the early 20th century, shortly after Einstein published his general theory of relativity, Theodore Kaluza and Oscar Klein independently proposed a theory that attempted to unify gravity and electromagnetism by introducing a 5th dimension. Their Kaluza-Klein theory suggested that if the universe had an extra spatial dimension, and if that dimension were curled up into a tiny, unobservable circle, then gravity propagating in this 5-dimensional space-time would appear, from our 4-dimensional perspective, to manifest as both gravity and electromagnetism. The strength of the electromagnetic force would be related to the size of this curled-up dimension. This was a groundbreaking idea, showing that seemingly disparate forces could emerge from a higher dimensional geometry. While Kaluza-Klein theory ultimately failed to fully unify all forces and predict the existence of all particles, it laid the conceptual groundwork for later theories involving extra dimensions. The key to understanding how extra dimensions could exist without being directly observable is the concept of compactification. Imagine a long, thin garden hose. From a distance, it looks like a one-dimensional line, but if you get very close, you can see that it has a second dimension, its circumference, curled up into a small circle. Similarly, physicists propose that extra dimensions might be curled up, or compactified, into incredibly tiny microscopic spaces, far too small for us to perceive directly with our current technology. These dimensions could be curled up into incredibly complex geometric shapes, often referred to as Calabi-Yau manifolds in string theory. The specific geometry of these curled-up dimensions would then dictate the fundamental physical laws and constants that we observe in our four large dimensions. The most prominent theory that necessitates extra dimensions is string theory and its more encompassing framework. M-theory. String theory proposes that the fundamental building blocks of the universe are not point-like particles, but tiny, one-dimensional, vibrating strings, unimaginably small. Different vibration modes of these strings correspond to different fundamental particles, such as electrons, quarks, and photons. For string theory to be mathematically consistent and free of anomalies, it requires the existence of 10 space-time dimensions. M-theory, which unifies various string theories, requires 11 space-time dimensions. The extra 6 or 7 spatial dimensions are thought to be compactified, curled up into complex Calabi-Yau shapes. The specific way these extra dimensions are compactified is crucial, as it determines the properties of the particles and forces we observe in our four-dimensional world. There are an enormous number of ways these dimensions can be curled up, estimated to be as high as 10 to the power of 500 different possible geometries. Each of these geometries would correspond to a different set of physical laws and constants. This vast array of possibilities is often referred to as the string landscape or the multiverse landscape. In this context, our universe, with its specific, fine-tuned laws, is simply one particular realization within this enormous landscape of possibilities, arising from a specific compactification of the extra dimensions. Another fascinating idea involving extra dimensions comes from brain cosmology, particularly models like the Randall-Sundrum models proposed in the late 1990s. In these models, our entire four-dimensional universe is envisioned as a brain, a higher-dimensional membrane embedded within a larger, higher-dimensional space called the bulk. In this scenario, ordinary matter and the fundamental forces are confined to our brain. However, gravity, unlike the other forces, is hypothesized to be able to propagate into the higher-dimensional bulk. This leakage of gravity into extra dimensions could explain why gravity appears so much weaker than the other fundamental forces from our four-dimensional perspective. The gravitational force we experience is only a fraction of its true strength, as much of its influence is diluted by spreading into the extra dimensions. This could potentially solve the hierarchy problem, which is the vast discrepancy between the gravitational scale and the electroweak scale. The search for experimental evidence of extra dimensions is a major frontier in physics. One approach involves looking for deviations from Newton's inverse square law of gravity at very small distances. If extra dimensions exist and gravity can propagate into them, then gravity's strength should increase more rapidly than the inverse square law at distances comparable to the size of these extra dimensions. Current experiments have tested gravity down to microscopic scales and have so far found no deviations, placing limits on the size of any large extra dimensions. Another avenue is to search for Kaluza-Klein particles at high-energy particle accelerators like the Large Hadron Collider. If extra dimensions are real, particles could have momentum in these curled-up dimensions, appearing to us as heavier versions of known particles. Detecting such particles would be a strong indicator of extra dimensions. Furthermore, some theories suggest that extra dimensions could affect the propagation of gravitational waves, offering another potential avenue for detection. If extra dimensions truly exist, they would radically alter our understanding of the universe. Our familiar four-dimensional spacetime would be merely a slice or a projection of a much grander, higher-dimensional reality. This would not only provide a framework for unifying all the fundamental forces, but also offer a compelling explanation for the fine-tuning of our universe's properties within the vast landscape of possibilities arising from different compactifications. The existence of dimensions beyond our perception would mean that the universe is even more intricate and mysterious than we currently imagine, constantly pushing the boundaries of our knowledge. The holographic principle is one of the most profound and counterintuitive ideas to emerge from theoretical physics in recent decades, suggesting that our three-dimensional reality might be, in some sense, a projection from a two-dimensional surface. The concept derives its name from a hologram, a two-dimensional photographic plate that encodes three-dimensional information, allowing a full, three-dimensional image to be reconstructed when illuminated correctly. In physics, the holographic principle posits that the description of a volume of space can be thought of as encoded on its boundary, much like a hologram. This means that all the information contained within a region of space, including everything inside it, could be entirely represented by data existing on its two-dimensional surface. This radical idea first emerged from the study of black holes in the 1970s and 80s. Stephen Hawking's work on black hole radiation and Jacob Bekenstein's insights into black hole entropy were pivotal. Bekenstein proposed that the entropy of a black hole, a measure of its internal disorder or the amount of information it contains, is not proportional to its volume, as one might intuitively expect for a three-dimensional object. Instead, he argued that a black hole's entropy is proportional to the area of its event horizon, the two-dimensional boundary beyond which nothing, not even light, can escape. This was a revolutionary idea because it implied that the maximum amount of information that can be contained within a region of space scales with its boundary area, not its volume. This concept was further developed by Gerard de 't Hooft and Leonard Susskind in the 1990s, who generalized it into the holographic principle. They argued that if the maximum entropy of a region of space scales with its boundary area, it implies that the fundamental degrees of freedom, the basic bits of information that describe everything, are not located throughout the volume, but are instead stored on the boundary. It's as if the entire three-dimensional reality of the black hole's interior is somehow encoded on its two-dimensional surface. This is deeply counterintuitive because our everyday experience tells us that a larger volume can hold more information than a smaller surface. For example, a three-dimensional book contains more information than its two-dimensional cover. The holographic principle suggests that, at the most fundamental level, this intuition is wrong for space-time itself. The most concrete and powerful realization of the holographic principle comes from the ADSI-CFT correspondence, or anti-de Sitter/conformal field theory correspondence, sometimes called Maldacena duality. Proposed by Juan Maldacena in 1997, this is a profound mathematical conjecture that states that a theory of gravity in a particular type of curved spacetime, called anti-de Sitter space, is mathematically equivalent to a quantum field theory living on its boundary, which has one fewer dimension. For example, a theory of gravity in a five-dimensional anti-de Sitter space is equivalent to a four-dimensional quantum field theory living on its boundary. This correspondence is a duality because it provides two entirely different, yet mathematically equivalent, ways to describe the same physical reality. One description involves gravity and extra dimensions, while the other involves quantum particles and forces in a lower dimension. It's like having two different languages that perfectly describe the same set of phenomena. The ADS/CFT correspondence has been incredibly fruitful for theoretical physicists because it allows them to use the well-understood tools of quantum field theory to study difficult problems in quantum gravity, and vice versa. For instance, problems in strongly interacting quantum systems, like those found in high-temperature superconductors, can be mapped to simpler problems in gravity in a higher dimension. The implications of the holographic principle for our own universe are profound. Though it is important to note that the ADS/CFT correspondence applies to anti-de Sitter space, which has a negative cosmological constant, whereas our universe has a positive cosmological constant and is expanding. However, many physicists believe that the holographic principle is a more general feature of quantum gravity, and that some form of it might apply to our universe as well. If the holographic principle applies to our universe, it would mean that all the information describing our four-dimensional spacetime and everything within it could, in principle, be encoded on a distant three-dimensional boundary. This does not necessarily mean that we live in a computer simulation in the way discussed in the previous chapter, but it implies a deep and unexpected relationship between space, information, and gravity. It suggests that the fundamental reality might not be what we perceive as three-dimensional space, but rather a more fundamental information-theoretic structure residing on a boundary. Our perceived reality would then be an emergent phenomenon, a holographic projection from this underlying information. This idea challenges our intuitive understanding of space as a fundamental container. Instead, space itself might be an emergent property arising from the entanglement of quantum degrees of freedom on a boundary. It suggests that the universe has a finite amount of information, and this information is stored on its surface, much like a cosmic hard drive. While direct experimental verification of the holographic principle in our universe remains a distant goal, it continues to be a powerful guiding principle. In the search for a unified theory of quantum gravity, offering a radical new perspective on the fundamental nature of reality and the very fabric of space-time, it hints that the universe's existence might be an intricate dance of information projected into the dimensions we perceive. At the very frontiers of our understanding of the universe lies a realm of existence so incredibly tiny and fleeting that our current theories of physics begin to break down. This is the Planck scale, a set of fundamental units of measurement length, time, mass, and temperature derived solely from universal physical constants, the speed of light, the gravitational constant, and the reduced Planck constant. These units, named after the pioneering German physicist Max Planck, who first introduced them in 1900, are not arbitrary. They represent the natural scales at which the effects of quantum mechanics and general relativity become equally important and inextricably intertwined. The Planck length is the smallest possible unit of length that has any physical meaning. It is approximately 1.6 times 10 to the power of minus 35 meters. To put this into perspective, if an atom were expanded to the size of the entire observable universe, a Planck length would still be smaller than a single atom. At distances smaller than the Planck length, the very fabric of spacetime is theorized to become so turbulent and foamy due to quantum fluctuations that our usual concepts of smooth space and time cease to apply. It is at this scale that the quantum nature of gravity, often referred to as quantum foam, is expected to manifest. Our current understanding of space-time, based on general relativity, describes it as a smooth, continuous manifold. However, at the Planck length, this smooth picture is expected to dissolve into a chaotic, probabilistic quantum realm. The Planck time is the smallest unit of time, approximately 5.4 times 10 to the power of minus 44 seconds. This is the shortest possible duration that has any physical significance. It represents the time it would take for light to travel one Planck length. In the context of the Big Bang, the Planck epoch, which lasted from the beginning of the universe up to one Planck time, is the earliest moment about which we can even theoretically speculate. Before this time, or within this incredibly brief interval, our current laws of physics are insufficient to describe what was happening. The universe was so hot and dense that quantum gravitational effects dominated, and space-time itself was likely in a state that defies our conventional understanding. The Planck mass is approximately 2.17 times 10 to the power of minus 8 kilograms, which is roughly the mass of a flea egg. While this might seem like a macroscopic mass compared to elementary particles, it is the mass at which a particle's Compton wavelength becomes equal to its Schwarzschild radius. In essence, a particle with the Planck mass, if compressed to the Planck length, would become a black hole. This unit is significant because it represents the scale at which the quantum effects of gravity become as strong as the gravitational force itself. Finally, the Planck temperature is an incredibly high temperature, approximately 1.4 times 10 to the power of 32 Kelvin. This is the maximum theoretical temperature representing the temperature of the universe at the Planck time. At such extreme temperatures, all known fundamental forces are believed to have been unified, and particles would have possessed energies far beyond anything we can recreate in laboratories. The significance of the Planck scale lies in the fact that it marks the boundary where our two most successful yet incompatible theories of physics, general relativity, describing gravity in the large-scale universe, and quantum mechanics, describing particles and forces at the microscopic level, both become relevant and equally important. However, these two theories, in their current forms, are not easily reconciled. General relativity describes gravity as the curvature of a smooth spacetime, while quantum mechanics describes particles and forces in terms of discrete quanta and probabilities. When one attempts to apply quantum mechanics to gravity, the calculations break down, leading to infinities that cannot be resolved. This fundamental incompatibility is the core reason why we lack a complete theory of quantum gravity. At the Planck scale, the very concepts of space and time as continuous entities may cease to be valid. Instead, space-time might be granular or foamy, composed of discrete units, much like a digital image is composed of pixels. This implies that there is a fundamental limit to how finely we can probe reality. We cannot meaningfully ask what happens at distances smaller than the Planck length or during intervals shorter than the Planck time, because the very notions of space and time lose their conventional meaning. The breakdown of physics at the Planck scale represents the ultimate edge of knowledge in our quest to understand the universe. It is the realm where the most fundamental questions about the origin of space-time, the nature of reality, and the unification of all forces must ultimately be answered. Theories like string theory and loop quantum gravity are attempts to construct a theory of quantum gravity that can describe physics at this extreme scale, providing a consistent framework that incorporates both general relativity and quantum mechanics. Understanding the Planck scale is not just an academic exercise, it is essential for a complete picture of the universe, including its earliest moments during the Big Bang and the ultimate nature of its existence. Despite the monumental achievements of science in unraveling the mysteries of the cosmos, humanity stands at a precipice, gazing into a vast expanse of the unknown. Our current scientific understanding, while profound, is far from complete. There are fundamental questions about the universe that remain unanswered, major phenomena that defy our current theoretical frameworks, and vast swaths of reality that lie beyond the reach of our present observational capabilities. This edge of knowledge is not a sign of failure, but rather a testament to the immense complexity of the universe and the ongoing nature of scientific inquiry. One of the most glaring gaps in our understanding is the nature of dark matter. We have compelling evidence for its existence from galaxy rotation curves, gravitational lensing, and the cosmic microwave background, indicating that it makes up approximately 27% of the universe's mass-energy content. However, we do not know what dark matter is. It does not interact with light or other electromagnetic radiation, which is why it is invisible. It also does not seem to interact strongly with ordinary matter. Despite decades of dedicated experiments searching for weakly interacting massive particles, or WIMPs, the leading candidate for dark matter, no definitive detection has been made. The identity of dark matter particles remains one of the most significant unsolved problems in particle physics and cosmology, representing a huge missing piece in our cosmic inventory. Equally perplexing is dark energy, which accounts for roughly 68% of the universe's total mass energy. Its existence was inferred from the accelerating expansion of the universe. Discovered in 1998, dark energy acts as a repulsive force, pushing galaxies apart, and its energy density does not dilute as the universe expands. The simplest explanation is that it is the cosmological constant, the intrinsic energy of empty space. However, theoretical calculations of this vacuum energy from quantum field theory predict a value that is an astonishing 120 orders of magnitude larger than what is observed. This cosmological constant problem is the largest discrepancy between theory and observation in all of science, indicating a profound misunderstanding of either quantum mechanics, gravity, or both. Its nature and origin are completely unknown, yet it dictates the ultimate fate of the universe. The unification of quantum mechanics and general relativity represents arguably the greatest challenge at the edge of knowledge. Quantum mechanics successfully describes the microscopic world of particles and forces, while general relativity accurately describes gravity and the large-scale structure of the universe. Both theories are incredibly successful within their respective domains, but they are fundamentally incompatible. When one attempts to combine them, the calculations break down, leading to infinities. This means we lack a complete theory of quantum gravity, which is essential for understanding phenomena at extreme conditions, such as the very first moments of the Big Bang or the interior of black holes. Theories like string theory and loop quantum gravity are ambitious attempts to bridge this gap, but they are still under development and lack definitive experimental verification. Beyond these major components, there are numerous other fundamental questions. The origin of the universe itself remains deeply mysterious. While the Big Bang theory describes the evolution of the universe from an extremely hot, dense state, it does not explain what caused that initial state or what existed before it. Was there a singularity? Did the universe emerge from a quantum fluctuation in a pre-existing multiverse? The very first moments, before the Planck time, are beyond our current theoretical grasp. Similarly, the matter-antimatter asymmetry, why our universe is overwhelmingly made of matter when equal amounts of matter and antimatter should have been created in the Big Bang, is an unsolved puzzle. The mechanisms that led to this tiny, crucial imbalance are not fully understood. The nature of consciousness is another profound mystery that bridges physics, biology, and philosophy. How does subjective experience arise from physical matter? Is consciousness merely an emergent property of complex neural networks, or is there a deeper, more fundamental connection to the fabric of reality? While neuroscience continues to make strides in understanding brain function, the hard problem of consciousness explaining why physical processes give rise to qualitative experience remains elusive. Furthermore, the universe might contain phenomena or dimensions that are currently beyond our ability to detect or even conceive. The possibility of extra dimensions, as proposed by string theory, or the idea that our universe is a holographic projection from a lower dimensional boundary, challenges our fundamental understanding of space and time. These concepts, while mathematically elegant, push the boundaries of empirical verification. The edge of knowledge is not a static line. It is a constantly shifting frontier. Each scientific breakthrough, while providing answers, often reveals new, deeper questions. The discovery of dark matter and dark energy, for instance, solved some cosmological puzzles, but introduced even larger ones. This ongoing process of discovery and the recognition of what we do not know are essential drivers of scientific progress. The vastness of our ignorance underscores the incredible complexity and mystery of the universe, reminding us that its existence and our ability to ponder it are perhaps the greatest mysteries of all. For centuries, physicists have dreamed of discovering a single, overarching theoretical framework that could explain all the fundamental forces and particles in the universe. This ambitious quest is known as the search for a theory of everything, or TOE. The goal of a TOE is to unify general relativity, which describes gravity and the large-scale structure of the cosmos, with quantum mechanics, which describes the other three fundamental forces and the behavior of matter at the microscopic level. Such a theory would provide a complete and consistent description of all physical phenomena, from the Big Bang to the present day, and from the smallest subatomic particles to the largest galaxy clusters. The history of physics has been marked by successful unifications. In the 17th century, Isaac Newton unified celestial mechanics with terrestrial mechanics under his universal law of gravitation. In the 19th century, James Clerk Maxwell unified electricity and magnetism into a single electromagnetic force, demonstrating that light itself is an electromagnetic wave. In the 20th century, the Standard Model of particle physics successfully unified the electromagnetic force with the weak nuclear force into the electroweak force, and it also describes the strong nuclear force. The Standard Model, confirmed by numerous experiments including the discovery of the Higgs boson in 2012, is an incredibly successful theory, describing all known elementary particles and their interactions, except for gravity. However, gravity remains the outlier. Albert Einstein's general theory of relativity, which describes gravity as the curvature of space-time, is a classical theory. It works exceptionally well on large scales, explaining the orbits of planets, the bending of light by massive objects, and the expansion of the universe. But when attempts are made to incorporate gravity into the quantum mechanical framework, the mathematical calculations break down, leading to infinities and inconsistencies. This fundamental incompatibility between general relativity and quantum mechanics is the central obstacle in the search for a TOE. A theory of quantum gravity is needed to describe phenomena where both gravity and quantum effects are significant, such as in the extreme conditions of the very early universe or within the singularity of a black hole. Several theoretical approaches are being pursued in the quest for a TOE. The most prominent and extensively studied candidate is string theory. String theory proposes that the fundamental building blocks of the universe are not point-like particles, but tiny, one-dimensional, vibrating strings, unimaginably small. Different vibration modes of these strings correspond to different fundamental particles and forces. A key feature of string theory is that it naturally incorporates gravity. One of the vibration modes of a string corresponds to the graviton, the hypothetical quantum particle that mediates the gravitational force. For string theory to be mathematically consistent, it requires the existence of more than the familiar 4 space-time dimensions. Most versions of string theory require 10 space-time dimensions, while its overarching framework, M-theory, requires 11 dimensions. The extra dimensions are thought to be compactified or curled up into incredibly tiny, unobservable spaces. String theory offers a compelling framework for unifying all four fundamental forces and all known particles within a single, consistent mathematical structure. However, it currently lacks direct experimental verification, as the energies required to probe the Planck scale are far beyond the capabilities of any foreseeable particle accelerator. Another leading candidate for quantum gravity is loop quantum gravity. Unlike string theory, which attempts to unify all forces, loop quantum gravity focuses specifically on quantizing gravity itself, without necessarily unifying it with the other forces initially. It proposes that space-time is not continuous, but is granular, or quantized, at the Planck scale. In this theory, space is made up of discrete loops or networks, and time also flows in discrete steps. This approach attempts to construct a quantum theory of gravity directly from the principles of general relativity and quantum mechanics. While loop quantum gravity offers a consistent picture of quantum space-time and has made progress in understanding black hole entropy and the Big Bang singularity, it also faces challenges, particularly in fully recovering classical general relativity at large scales and in making testable predictions. Other approaches to quantum gravity include causal set theory, which posits that space-time is fundamentally discrete and that events are ordered by a causal relationship. Non-commutative geometry, which suggests that space-time coordinates do not commute at the Planck scale. And twistor theory, which attempts to reformulate physics in terms of fundamental geometric objects called twistors. Each of these theories offers a unique perspective on how to reconcile gravity with quantum mechanics, but none has yet achieved the status of a fully verified TOE. The search for a TOE is driven by the belief that the universe should ultimately be governed by a single, elegant, and consistent set of laws. Such a theory would not only provide a deeper understanding of the fundamental nature of reality, but could also offer insights into some of the most perplexing mysteries in cosmology, such as the origin of the universe, the nature of dark matter and dark energy, and the ultimate fate of the cosmos. It would allow physicists to describe the universe from the very first moments of the Big Bang, where all forces were unified, to its present state, and potentially predict phenomena beyond our current observational capabilities. However, the path to a TOE is fraught with challenges. The extreme energies and incredibly small scales at which quantum gravitational effects become dominant make direct experimental verification exceedingly difficult. The mathematical complexity of these theories is also immense. Despite these hurdles, the pursuit of a TOE remains the ultimate goal for many physicists, representing the pinnacle of human scientific endeavor. A quest to find the single, unifying principle that explains why the universe exists and how it all works. The search for one continues, pushing the boundaries of human intellect and revealing the profound depths of cosmic mystery. The universe operates with remarkable regularity and predictability, governed by a set of fundamental principles that physicists refer to as the laws of nature. These laws, expressed most precisely through the language of mathematics, dictate how matter and energy behave, how forces interact, and how the cosmos evolves. From the smallest subatomic particles to the grandest galaxy clusters, these laws appear to be universal, applying consistently across vast distances and immense timescales. They are unchanging, meaning the laws that govern the early universe are the same laws that govern it today, and they are deterministic in many contexts, allowing scientists to make precise predictions about future events. Yet, despite our increasing understanding of what these laws are and how they work, a deeper, more profound question remains: what is the origin and fundamental nature of these physical laws themselves? Are they arbitrary, a mere cosmic happenstance, or is there a deeper reason for their specific form and existence? One perspective views the laws of nature as inherent, fundamental properties of reality. In this view, they are not imposed from outside the universe, but are intrinsic to its very fabric, existing independently of any particular universe or observer. They are seen as necessary truths, perhaps even part of a larger, purely mathematical structure that simply is. This idea resonates with the unreasonable effectiveness of mathematics in describing the physical world. As noted by the physicist Eugene Wigner, if the universe is fundamentally mathematical, then its laws are simply expressions of that underlying mathematical reality. This perspective suggests that the laws could not have been otherwise. They are the only possible, consistent set of rules for a universe to exist. However, this raises the question of why these specific mathematical structures are realized, and why they are so perfectly conducive to complexity and life. A point that connects directly to the fine-tuning puzzle. Another viewpoint suggests that the laws of nature might be emergent properties, arising from a deeper, more fundamental level of reality. For instance, in some theories of quantum gravity, such as loop quantum gravity or certain approaches within string theory. Space-time itself is not a fundamental, continuous background, but an emergent phenomenon built from more basic, discrete components. If space-time is emergent, then the laws of physics that operate within it might also be emergent, arising from the interactions of these more fundamental constituents. This would mean that the laws we observe are not truly fundamental, but are effective descriptions that apply at our particular scale of existence. This perspective offers a potential pathway to explain why the laws have their specific form. They are the macroscopic manifestation of simpler, underlying rules at the Planck scale. However, this merely pushes the question back a level. What are the laws governing these more fundamental constituents, and why do they exist? The concept of symmetries plays a crucial role in understanding the nature of physical laws. Many fundamental laws are deeply connected to symmetries in nature. For example, the conservation of energy is a consequence of the laws of physics being the same at all times. The conservation of momentum arises from the laws being the same at all locations in space. The conservation of angular momentum is linked to the laws being the same regardless of orientation. These symmetries are not just mathematical curiosities. They are profound statements about the universe's inherent order and consistency. But why does the universe possess these particular symmetries? Are they arbitrary choices, or are they somehow necessary for a consistent reality? The existence of these symmetries, which are beautifully described by group theory in mathematics, further blurs the line between a universe described by mathematics and a universe that is mathematics. The fine-tuning of the universe's constants, as discussed previously, adds another layer of complexity to the question of the nature of laws. If the laws are fixed and necessary, then their specific values, which appear so precisely calibrated for life, seem like an astonishing coincidence. If the laws are arbitrary, then their life-permitting values are an even greater coincidence. The multiverse hypothesis offers a potential resolution by suggesting that our universe is just one of many, each with different laws or different values for constants. In this scenario, the laws of our universe are not arbitrary in the grand scheme, but are simply one set among a vast ensemble. We observe these specific laws because only they permit our existence. However, this then raises the question of the meta-laws that govern the multiverse itself. What determines the distribution of laws across different universes? Are these meta-laws themselves arbitrary or necessary? The limits of scientific inquiry also come into play when pondering the nature of laws. Science excels at describing what the laws are and how they operate through observation, experimentation, and mathematical modeling. It can tell us that gravity follows an inverse square law, or that particles obey quantum mechanical rules. But science, by its very nature, is less equipped to answer the ultimate why questions. Why do these laws exist in the first place? Why are they the specific laws that they are? This question often pushes into the realm of metaphysics and philosophy, beyond the empirical reach of current scientific methods. Some physicists argue that the laws simply are, that they are brute facts of existence for which there is no deeper explanation. Others continue to search for a more fundamental principle from which all laws could logically derive, perhaps a theory of everything that reveals a deeper, unavoidable necessity for the observed laws. The very concept of a law implies a regularity, a pattern that repeats. Without such regularities, the universe would be chaotic and unpredictable, making scientific understanding impossible. The fact that the universe adheres to these consistent mathematical rules allows for the emergence of order, complexity, and ultimately, consciousness capable of discerning these very laws. Whether these laws are fundamental, emergent, or selected from a larger ensemble, their existence and specific form are central to the universe's ability to exist in its currently observed, life-permitting state. The ongoing quest to understand the nature of these laws is a testament to humanity's enduring curiosity about the deepest foundations of reality. The universe, while governed by precise and consistent physical laws, also exhibits an undeniable element of randomness or chance. This interplay between determinism, where future states are perfectly predictable from initial conditions, and indeterminism, where outcomes are inherently probabilistic, is a profound aspect of reality. Understanding how much of what we see is due to fixed laws versus unpredictable chance events is crucial for a complete picture of the cosmos and our place within it. In classical physics, particularly the mechanics developed by Isaac Newton in the 17th century, the universe was largely seen as a deterministic clockwork. If one knew the precise position and momentum of every particle in the universe at a given instant, and all the forces acting upon them, then the entire future evolution of the universe could, in principle, be perfectly predicted. This idea was famously encapsulated by Pierre-Simon Laplace in the early 19th century, who imagined a hypothetical demon with such immense knowledge and computational power that it could foresee every event, past and future. In this classical view, chance was merely a reflection of our ignorance, a practical limitation on our ability to know all the necessary initial conditions. However, the advent of quantum mechanics in the early 20th century fundamentally challenged this classical deterministic worldview. At the microscopic level of atoms and subatomic particles, quantum mechanics introduces an inherent, irreducible randomness into the fabric of reality. This is not due to our lack of knowledge, but rather a fundamental property of nature itself. One of the cornerstones of quantum indeterminism is the Heisenberg uncertainty principle, formulated by Werner Heisenberg in 1927. This principle states that there are certain pairs of properties of a quantum particle, such as its position and momentum, that cannot be known simultaneously with arbitrary precision. The more precisely you measure one, the less precisely you can know the other. This means that even if you knew everything possible about a particle at one moment, you could not perfectly predict its future trajectory, because its initial position and momentum cannot be simultaneously known with infinite precision. Furthermore, quantum mechanics describes particles existing in a superposition of multiple possible states until they are measured or observed. When a measurement is made, the wave function describing the particle's possibilities collapses into a single, definite outcome. The specific outcome that occurs is fundamentally probabilistic. For example, a radioactive atom undergoes decay at a fundamentally random moment. While we can predict the half-life of a large sample of radioactive atoms, we cannot predict when any single atom will decay. This is not because we lack information about the atom, but because the event itself is inherently random at the quantum level. This quantum randomness is a genuine, irreducible element of chance in the universe. While individual quantum events are fundamentally random, their effects often average out at macroscopic scales. The vast number of particles involved in everyday objects means that their collective behavior often appears deterministic. For example, while the decay of a single radioactive atom is random, the overall decay rate of a large sample of atoms is highly predictable. This is why classical physics works so well for macroscopic phenomena. However, there are instances where quantum randomness can have macroscopic consequences, particularly in highly sensitive systems. The role of chance is evident throughout cosmic evolution. The very seeds of large-scale structure in the universe, the tiny density fluctuations from which galaxies and galaxy clusters eventually grew, are believed to have originated from random quantum fluctuations in the very early universe, stretched to cosmic scales by inflation. These random quantum events, amplified to macroscopic scales, determined where the first stars and galaxies would form, and thus the overall distribution of matter in the universe. On Earth, biological evolution is a prime example of the interplay between chance and law. Genetic mutations, which introduce new variations into a population, are largely random events at the molecular level, often caused by errors in DNA replication or exposure to radiation. These random mutations provide the raw material for natural selection to act upon. Environmental changes, such as asteroid impacts, volcanic eruptions, or climate shifts, can also be viewed as chance events that drastically alter the course of evolution, leading to mass extinctions or new adaptive opportunities. The laws of natural selection then provide the deterministic framework for which traits are favored and how populations evolve over time. Without the element of random mutation, evolution would grind to a halt. Even in seemingly deterministic systems, chaos theory reveals how tiny, unpredictable variations in initial conditions can lead to vastly different outcomes over time. The butterfly effect, where a butterfly flapping its wings in Brazil could theoretically cause a tornado in Texas, illustrates how complex systems like weather patterns are inherently unpredictable in the long term, even if their underlying laws are deterministic. This is a form of practical unpredictability, distinct from the fundamental quantum randomness, but it highlights how chance can play a significant role in the unfolding of events. Ultimately, the universe appears to be a grand tapestry woven from threads of both fixed laws and unpredictable chance. The fundamental laws of physics provide the framework, the rules of the game, defining the possibilities and constraints for what can happen. They dictate how particles interact, how forces operate, and how space-time behaves. But within this framework, quantum randomness provides the inherent unpredictability at the most fundamental level, while chance events on larger scales introduce contingencies that shape the specific unfolding of cosmic and biological history. The universe is not a perfectly predictable machine, but a dynamic system where the interplay of law and chance leads to the rich, complex, and often surprising reality that we observe. The universe, at its most fundamental level, is described by a relatively small set of elementary particles and fundamental forces. Yet, from these simple building blocks and their interactions, an astonishing array of complex patterns, structures, and phenomena arise. This process, where intricate properties and behaviors emerge from the collective interactions of simpler components, is known as emergence. It is a concept that bridges different levels of scientific inquiry, explaining how the universe, despite its underlying simplicity at the deepest scales, can produce the incredible complexity we observe, from stars and galaxies to life and consciousness. Emergence means that the whole is greater than the sum of its parts. The properties of the complex system cannot be simply deduced by examining its individual components in isolation. A classic example of emergence comes from thermodynamics. The concepts of temperature, pressure, and entropy are not properties of individual atoms or molecules. A single atom does not have a temperature. However, when a vast number of atoms or molecules interact, their collective motion and collisions give rise to these macroscopic properties. Temperature, for instance, emerges from the average kinetic energy of the particles in a system. Pressure emerges from the force exerted by these particles colliding with the walls of a container. Entropy, a measure of disorder, emerges from the statistical arrangement of countless particles. The laws of thermodynamics, which describe how heat flows and how systems tend towards equilibrium, are emergent laws that arise from the underlying statistical mechanics of microscopic particles following simple rules of motion. In chemistry, the properties of molecules are emergent from the interactions of individual atoms. A water molecule, composed of 2 hydrogen atoms and 1 oxygen atom, has properties like being a liquid at room temperature, its solvent capabilities, and its high specific heat capacity that are entirely different from the properties of isolated hydrogen or oxygen atoms. These emergent properties arise from the specific electromagnetic bonds formed between the atoms and the resulting molecular structure. Furthermore, the self-assembly of complex biological molecules, such as proteins folding into intricate, 3-dimensional shapes, or lipid molecules spontaneously forming cell membranes, are powerful examples of emergent order from simpler chemical rules. Perhaps the most profound example of emergent order is the emergence of life from non-living chemistry. Individual atoms and molecules are not alive. However, when vast numbers of specific molecules, such as DNA, proteins, lipids, and carbohydrates, interact in highly organized ways within a specific environment, they give rise to the emergent properties of life metabolism, reproduction, self-organization, and evolution. A single cell, a marvel of emergent complexity, operates through intricate networks of chemical reactions and molecular machinery, none of which, in isolation, possesses the property of life. Life emerges from the collective, dynamic organization of these non-living components on a larger scale. Consciousness is believed by many to be an emergent property of the incredibly complex network of neurons and their interactions in the brain. Individual neurons are simple, biological cells that fire electrical signals. However, when billions of these neurons are interconnected in intricate ways, forming vast neural networks with trillions of synapses, the emergent phenomenon of subjective experience thought, emotion, and self-awareness arises. We cannot find consciousness by looking at a single neuron. It emerges from the collective activity of the entire system. In cosmology, the large-scale structures of the universe are emergent. The universe began from an almost perfectly uniform, hot, dense plasma. Over billions of years, gravity acting on tiny, initial density fluctuations caused matter to clump together. This process led to the emergence of stars, which are highly ordered, self-gravitating spheres of plasma. Stars then clustered into galaxies, which are vast, rotating systems of billions of stars, gas, and dark matter. Galaxies, in turn, are organized into galaxy clusters and superclusters, forming a vast, filamentary cosmic web. These hierarchical structures are emergent properties of the interplay between gravity, dark matter, and the expansion of the universe, arising from simple initial conditions and fundamental laws. The concept of emergence highlights that complexity does not necessarily require complex fundamental laws. Often, simple. Underlying rules, when applied repeatedly to a vast number of interacting components, can lead to surprisingly intricate and unpredictable patterns. Think of a cellular automaton like Conway's Game of Life, where simple rules for how cells turn on or off based on their neighbors lead to incredibly complex. Evolving patterns, including self-replicating structures, these systems demonstrate how local interactions can give rise to global order. Emergence is not a violation of the second law of thermodynamics, which states that total entropy tends to increase, while local pockets of order, like a living organism or a star, represent a decrease in entropy. This local decrease is always compensated by a much larger increase in entropy in the surrounding environment. For example, A star creates order by fusing light elements into heavier ones, but it radiates vast amounts of high-entropy energy into space. A living organism maintains its internal order by consuming low-entropy food and releasing high-entropy waste products and heat. The universe as a whole continues its march towards increasing disorder. But within this overall trend, pockets of remarkable order and complexity can emerge and persist for long periods. The universe's capacity for emergent order is a key reason why it is not just a featureless expanse, but a dynamic, evolving cosmos filled with diverse phenomena. It explains how, from a relatively simple beginning, the universe has unfolded into the rich, structured, and conscious reality that we observe. The existence of emergent order is a testament to the power of fundamental laws to generate complexity, making the universe's very existence and its ability to produce such intricate patterns a profound and beautiful mystery.